plays Q in John Cleese. So he could have said John Cleese because in James Bond, Q is played by John Cleese. Yeah.
Oh, I forgot all about that one. Thank you for reminding me.
That was one of the worst renditions of Q ever. I erased that.
It was. Who was the one before him? He was quite good. The old
Desmond Llewellyn.
There we are. See, so we could have said Desmond Llewellyn. I blame Desmond Llewellyn.
Was he still alive when he was replaced?
Yes.
Why didn't they get him back?
Because he was starting to dodder around. He was quite clearly much too old. In fact, in the last film he was in, along with a couple of others, they were all looking much too old for their roles.
Well, John Cleese was dreadful, though. I mean, John Cleese was not a good.
Was appalling. Yes,
he was just like hamming it up, wasn't he? It was a comedy performance.
Well, it was a comedy film. The idea of an invisible car running around in the ice was so ridiculous. I mean, I know it got gadget obsessed earlier, but this was just taking it to a level of ridiculous.
It was ridiculous. I agree. Was Roger Moore the Bond in it? Was he? Was it?
Roger Moore? It was Pierce Brosnan.
Oh, all right.
Another Day, the worst Bond ever made.
I didn't like Pierce Brosnan in any of the James Bond movies.
No, I agree.
Really.
He's a good actor, actually. Though. I quite like him in other things. Yeah,
he is,
but not as Bond.
But because of his religious views, he actually didn't pour himself into the role like he normally would, because he didn't like the whole fact that James Bond is literally the world's epitome of a womanizer.
Mm.
So he didn't actually like doing.
I wonder why he took the part in the first place, then, Shawn. Really,
it's all about the money.
I tell you what, the Thomas Crown Affair, that's a good film. If you've seen him in there, that's worth watching if it's on.
I haven't seen that one.
You've not seen Thomas Crown Affair where they well, I won't spoil it for you, but there's a painting involved, and if you see it,
the original one.
There's the original one is good, but also the remake with Brosnan is very good.
I liked it when John Cleese played. I liked it when John Cleese played Mr. Hilter.
The internal
chat.
Yeah,
Mr. Hilter.
I hit them before you did, Terry. It's all good.
Okay.
Yeah.
So are we across now? Or
That's good. Yeah.
Do we need to go on that link, Terry?
I think that was the north.
Just stay where you are.
All right. Okay. Right. You can complete now, Rumpus. We've transferred apparently.
Oh, right, yes. Mr. Hilter was when John Cleese, I don't know whether the reference, a Monty Python reference, when was a by-election in North Devon somewhere, or Minehead, I think it was, in North Devon, and he played Mr. Hilter along with everybody else, playing various, the Gestapo and Goebbels and God knows what. I don't think it did Goebbels, it was, oh God, what were the other characters in that particular sketch? There's, Chappie.
So you've twice got to the point, and we're on tenterhooks about what exactly is going to happen that Boris Johnson did or didn't need to do, and that's as far as you got.
Right. Before Alan bloody mutes me yet again, I was saying that Boris Johnson declared in Parliament that he was not going to make the application for an extension for membership of the EU, yet there is a law now in place, because he's in a minority government that was put there
the Ben Surrender Law.
The Ben Surrender Law, indeed, which is obliging him to request an extension for membership of the EU. So we now have what appear to be two incompatible statements, one by him and one,
but they got a way out of it because they think that someone else can sign the extension, don't they? The Solicitor General Attorney or something.
Well, no, I don't think. No, I don't think he's trying to suggest that someone else will do it on his behalf. No. The suggestion is that because he then said we will still leave on October the 31st, so which would.
Well, he's got to get a deal. He must have a deal in his.
No, I don't think that's going to happen. There's not enough time. So he's not going to ask someone else to do it because he's still going to leave on October the 31st, apparently, according to him. And there's a law in place saying if we don't have a deal, he has to request an extension. So these two things are incompatible. But he said it. He said he won't ask, and there is a law in place that tells him he has to ask. So one of those, something has got to give. We don't quite know what. There's some
Boris
suggestions.
Will weasel out of it, but Boris will get someone else to sign it, I reckon.
No, you don't seem to understand. He still said we would leave on October the 31st. Come up with that. That is not compatible with him saying there was getting someone else to do it. Because
you're right.
That's not going to get him out of it. So we're going to leave, apparently.
I tend to ignore the politics issues in my own country, and I have even less interest in politics of other countries, so I'm going to bow out.
Yeah, well, it's not quite as offensive. We haven't quite got a Trump yet, so that's it's not quite as annoying as American politics. But we do seem to have an incompatibility between two positions, which would be very interesting to see. Oh, there's some suggestion that there's a suggestion called the Privy Council, made up of members that have been appointed by the Queen, can briefly suspend some legislation if the circumstances merit it, there is some law on the statute book that allows the suspension of a law, but it only occurs in the state of an emergency, which we don't have. So that's the supposed current way he might get out of it. Anyway, getting back to normal conversation.
And that's the effect that it has at most dinner parties as well. So
no, normally, talking about Brexit normally gets people very excited.
Depends which side of the politics you come from. If you're a lefty like me, red under the bed and all that. What was I going to say? Something important about Flat Earth. I've forgotten now. Just thinking about Corbyn and dreadful man.
Yes, a pro-IRA, pro-Hamas, anti-British, wants to abolish the British Army, pro-Putin, terrorist supporting, attended a Palestinian memorial to the terrorists of the Munich attack and the Olympic Games in Munich, and supports Hamas, supports Iran, supports the IRA, used to sing IRA terrorist songs as a child, hates Britain. I think I've covered most of it there.
I've just remembered what it was.
Anti-nuclear. Yeah.
Are you not due to have a big debate with QE somewhere on a neutral territory? Because did he not call you out the other day?
No, he did.
Well, have I got that wrong?
I don't know. No, he's going to revive a debate we had about 3 years ago, in which even the flatties were asking him to shut up and go away, which I thought was quite amusing. And he did so bad. I mean, just appallingly. He was absolutely appalling in it. And I keep on challenging him, and he's never debated ever since. I beat him up so badly, it would seem, that he's never recovered from it. He's never ever debated with anybody ever again, and he refuses to all challenge. I mean, George publicly challenged him in Ranty's channel to a debate, and someone else did, and I happened to post in the side chat in Nathan's thing I went to there the other day, and I challenged.
I was there too. I saw it because he said.
That's right. Yeah, you were there.
Do you remember they were going about crickets, and at the end, then he also brought me in, which is why I'm doing my laser refractometry thing. And I've actually contacted. Did you hear that earlier? I contacted someone from McDonald Observatory, and I've actually got them to send me all their pictures. Yeah. So basically, what happened is he called me out at the end of the thing, didn't he? He said, Tony Liar tells us, MIT bounced something off the moon in 1962. So what he effectively did there is, on Nathan's show, he's told us that the moon is a physical object because MIT bounced something off it in 1962, which indeed they did. He's not wrong about that. They did. But that doesn't disprove that in 1969 and then all the way up to 2015, we haven't also been bouncing it off the moon, and especially off the retroreflectors, right? Because you can see the signal from the noise, and I've got really good evidence of that. So what I did is I reached out to a physicist at James Barrett, I think it's called, at McDonald Observatory, where they do these tests using these high-power lasers. And he's given me all the pictures.
It's one super high-powered laser, and it's not just.
There is, and they've got a very big telescope to collect all the light that comes back from it. Because when it actually hits the moon, it's 7 kilometers across. I didn't realize this because I was, interested in how they did it. Now, the killer is this, Rumpus. I'm going to go through the whole thing, prove that there actually are reflectors on the moon, when they were put there, where they were put, and I've got some results right from the experiments as well. So it's a nice little video piece that proves QE mistaken. Yeah. And thanks QE for affirming the moon's there. But at the end, I didn't realize it brings gravity in, because what they actually use it for now is to look at general relativity, and the SCP state. So it comes into it at the end.
I didn't know that, right?
No, I didn't realize. Yeah. So what they're doing, if you think about it, and I'd never realized this before, they where the observatory is and where they got the mirror, and then the moon. Now the moon is relatively stable, though they have apparently these lunar tides. There's lunar tides that affect the moon, and so the crust of the moon does flex up and down a bit, but that's only about, I think, 4 centimeters of drift. The bigger drift is on the Earth, because we get effects from the sun, believe it or not. So it's only 2 centimeters, but the sun actually affects the movement. Continental drift affects it, because what you actually want to do for these experiments to do with relativity is you want to take the center of the mass of the moon and the center of the mass of the Earth. So where you've actually placed your thing that's bouncing the signal up and then getting the signal back, usually that distance from the center of mass is really important. And so there's about
when you say, I thought the Earth went up and down depending on the position of the moon by about a foot or so.
Well,
I thought
there's 8 effects, and I'm not looking at it. It's not in front of me at the moment, right? But it's got all the quantities on it because he gave me the actual quantities of which the movements are. And as I say, the sun is very small. It's only about 2 centimeters. The solar radiation that hits the Earth, continental drift, they take into account.
So you said the solar radiation is changing the shape of the Earth.
Correct. So it's amazing. So they've got these. So there's about 10 different things that changes basically the position of that laser and of the thing, the mirrors that catch the signal coming back.
That doesn't say change the shape of the Earth. That could change the position of the Earth. The solar radiation
it changes the position. Hang on, it changes the position between the center of mass and where you're getting your signal and your reflection from. So imagine where the observatory is, right, on top of a mountain, and that's why they put them on mountains, right, because they're pretty solid things, generally. They don't move a lot, And so ideally, when you're doing your relativity experiment, you want to get it down to nanometers, right? So you've got the center of mass of one, center of mass of the other. But unfortunately, if your observatory is bouncing up and down, so imagine a big truck comes along the road and your mirrors bounce up and down a bit, that obviously messes the signal up because you don't know.
I still haven't quite this out. What are you saying that the solar radiation doing? Is it pushing the Earth slightly further away from the moon, therefore the distance to the moon changes, or are you claiming it's changing the shape of the Earth, which is what we were talking about when you said it's the 2 centimeters? I thought you were
need to look it up. It's no. It's only 2 centimeters of the solar radiation, and they list the effects. I'd need to read them up again. I've got detailed descriptions of what each effect is. Yeah, I'll do it while I'm here. Don't worry. Carry on talking, Barney, and I'll look up what the effects are so I can tell.
I was going to ask the same question. Maybe the thing that seems kind of an obvious jump for me is to say solar gravitation, maybe, because the sun does cause tides on the Earth.
Tides, no. I'll give you the list. Hang on.
Wait. And tides do affect solid surfaces.
Yes.
Right. It the gravitational pull of the sun and the moon distorts the shape of the Earth.
Yes,
that's right. I've got my presentation up. So now I'm going past all the lovely pictures of lasers that this guy sent me. By the way, he's given me some really great stuff.
Sounds really interesting. In fact, there are 10 effects. But you said solar radiation.
Here we go. So hang on. I'll give you the full bit. Here's the brief bit, right? This is the Apollo Observatory, the McDonald Apollo Observatory, right? So it's an incisive probe for gravity. Didn't realize that.
It's a what, sorry?
It's an incisive probe for gravity. Any known general relativity alternates violate the strong equivalence principle, whatever that means. 1 millimeter ranging improves constraints by 10 times. So basically that's why they built this one about 15 years ago. Geometrology and models account for the contamination effects. So they call them contamination effects, what we're about to talk about. Clearly, the precision measurement of the distance between the observatory and the LLR on the moon shows these relativity elements. The main challenges, and I will list the other challenges as well, but the main ones are as follows. Lunar crustal tides, up to 4 meters variation. Earth crustal tides, 20 centimeters variation. Solar radiation pressure, 4 millimeters, and now I'll go into the detail of those. The pressure of sunlight pushes the moon's orbit slightly off center. This is a small effect, about 3.65 millimeters, but it's particularly important since it mimics the effect of an EP violation. Continental drift must be compensated for.
Right, so it's not changing the shape, as I said. You seem to be implying
that
changing the shape.
Well, that's why I went to look.
It's not changing the shape; it is moving the moon.
That's why I went to look at the facts and give you the facts, right? Because you know me, I like to get it right. Otherwise one gets it wrong. The Earth's short-term weather can also affect the location of the telescope, primarily vertically. Various weather effects can load local regions of the Earth's crust, depressing the crust by a few millimeters. These effects come from the atmosphere, high-pressure systems press on the Earth's surface, and the ocean. Water piles up on the coast, depressing the crust. Groundwater fluctuations caused by rain can also affect the location. The Earth's crust changes in response to long-term fluctuations such as post-glacial rebound and loading caused by sediment. And the station also moves due to the tides. The moon, since it's tidally locked to the Earth, has relatively small and repeatable tides of about 10 centimeters, so they can account for that. The solid Earth has larger tides, oscillating about 35 centimeter peak to peak every 12 hours. And then they go into the polar axis. So it's really interesting if you think about it. It's amazing they can ever get a good standard reading. Do you see what I mean? Between the moon and Earth, because all these things are changing all the time.
Yeah,
well, they're going to have to count for all these effects, aren't they? And they say
but you can just say
nanometers.
But if you get all these other effects going on periodically, you can sort of say, okay, now the Earth goes up and down by 20 centimeters, depending through tidal effects, and then you obviously then get the distance to the moon, and if the distance to the moon changes uniformly across all these things by 3 centimeters per year, then you can identify that all these effects. The graph will go up and up and up, carrying on getting bigger. So although it's wobbling it's wobbling in between those things. So you might get a 20 centimeter change, but at least you can see that it's a wave on this generally increasing effect of the actual moon actually moving away. So it's not perhaps as challenging as you're suggesting, but yes, you've got to look for a 2 centimeter signal.
Yeah, hang on. I don't know how they get to 2 nanometers accuracy, bounce a signal off the moon. How can they tell the difference in that when they're looking at the relativity effects between that and, let's say, I don't know, whatever we said, tidal crust loading? It's rained a bit in California.
What are the relativity effects?
This is what they're looking for. This is the bit that I didn't realize. The reason they're doing all this laser ranging isn't just to know how far the moon is. They're actually investigating these relativity effects to do with the strong equivalence principle and general relativity.
Which is a strong equivalence.
You should look it up. It blew my mind. Basically, my whole presentation is about debunking. What's he called? So I got to go for tears. Debunking QE, and then right at the end, I suddenly found actually it's all about proving relativity and gravity.
Tori, can you repeat the lunar crust tidal range?
Yes, I was interested in that as well.
Did you say it was 4 meters? Did you say?
Yeah. Hang on, let me look them up again. I've got to open the thing again. Sorry.
20 centimeters lunar and 4 millimeter. No, sorry. 4 meters.
Lunar crustal tides 4 meters.
4 meters and
20 centimeters. Solar radiation pressure 4 millimeters. 3.65 actually, if you look at it. If you go to you can look. If you look up Laser Ranging Station Apollo, I think on Wiki, it's got a lot of information about it. So I've extracted stuff from Wiki and also from all the stuff he sent me, because he sent me pictures of the telescope. The laser firing up is green, actually. It's really exciting. And when it fires up...
Yeah, it's green, yeah.
Yeah, as I say, it's going to be a great video, honestly. I've done quite a bit of research on it now. So
it's really interesting.
Yeah, it is. I didn't realise gravity was going to be a gotcha there. I've just got to drop off because I've got to go and have tea. But I will be back. I will be back.
Bring a note.
Who was asking about the the lunar tidal behaviour? Was that John?
Yeah.
Yeah. So that's caused presumably just by interactions with the moon, the Earth, and the sun. The sun doing that. If it was just the
those would be the Earth tide on the.
Yeah, it's the equivalent of the tides in the ocean on the Earth. Of course.
There's a big difference there because because the moon's tidally locked, it's not going to move. The Earth moves, has a tidal up and down because it's rotating, and therefore there are bits moving up and down all the way through its orbit. Whereas the moon, because it's following the Earth and doesn't change its face, the tidal effects.
No, but it does have an elliptical orbit.
Sorry, what's it for the moon?
Perigee and apogee. So it's closer and further away. So there is a it's the same as it's exactly the same thing as that happens with Io. It's just a contraction and expansion, expansion.
Is that an elliptical orbit then?
Well, all orbits are elliptical. If it changes, if it was a perfect circle, there wouldn't be. There wouldn't be an increase and decrease in distance.
Yes,
and that is
some orbits are pretty close to being circular.
Yeah, pretty close. Yeah, but I don't think there is such a thing as a perfectly circular orbit.
So you're saying, hold on. So you're saying that the tidal effects on Io are a result of its elliptical orbit. Is that correct?
Yeah, because if it had a perfectly circular orbit, there wouldn't be any effect. There wouldn't be any increase or decrease.
It had a perfectly circular orbit and was tidally locked.
Yes. Yes, the tidal lock. I mean, obviously, it'd be tidally locked, something of that size. I thought the Io one was partly due to the other moons interacting with it.
Well, there's.
And I would have thought the thing occurred with the moon. That I accept that the elliptical orbit of the moon will cause it to be closer and further away, and that will cause something. But I would have thought also its position relative to the sun. The sun, I would have thought, also be due to the sun-moon interaction. But it's very different to the Earth one, which is what you seem to be saying earlier, because it is tidally locked to the Earth. It can only be an issue to do with its orbit and the distance to the Earth and the sun, whereas the Earth's tidal thing is a result of its rotating with respect to the moon.
Yeah.
So it's quite different.
The Galilean moons, there is quite a, well, it's probably common throughout other systems, but the Io, Europa, and Ganymede are in a 1-2-3 resonance, or 3-2-1 resonance.
That's right. Yes.
So there is. I don't really know much more about the effects of that on the tidal forces that the Io experiences, but yeah, it's quite a nice little quirky clockwork thing going on there. But yeah, I've always thought the tides on the surface of the moon are quite a sort of mind-boggling kind of thing to consider.
Actually, it does say here that indeed the elliptical nature of Io's orbit is actually the result of the tidal heating. Actually, so yeah, you were right there.
Yeah, but it's a permanent expansion and contraction due to the elliptical orbit, in particular of its orbit around Jupiter.
Well, it's not permanent, is it? It's a changing. Oh, okay, so it's continuously changing.
Yeah. Oh no, I didn't say permanent. But, well, I didn't mean to. If I did, but yeah, it's continually cyclic.
Yeah. So, but you were right. It is actually due to its eccentric orbit that seems to be the main cause of that.
Yeah, and there is because of the tidal range on the moon's surface, it's not completely geologically dead. It's if it was on its own, it would be, but because of the there is this slight sort of geological activity.
Yes, I've heard about that as well. Yes,
it's and so you get something called what's it called, transient lunar phenomena, where you get like outgassing, and so you could occasionally see if it's a big effect, you actually see a sort of haze of gas in some of the craters.
We're talking about the moon here.
Yeah.
All right. I thought you said
that. So there's, but it's such a rare event that you've got to compare. And there's big changes in libration, which can produce strange shadow effects. So you got to like reference the exact libration that you're seeing with another previous time that it occurred to double check that it's not just the effects of shadows or something.
Yeah.
So there are some people. I don't know anyone who does it, but there's a huge database of all the different librations of the moon that you can sort of cross-reference to make sure that you're actually seeing something that's outgassing or something.
Yeah, I mean, the movement of the moon is incredibly complicated. I remember talking about this with Quartus. It's about the equation to actually give you the motion of the moon with respect to the Earth is something like, I think I read it's a 200-line mathematical equation to model it or something. It's just
yeah. Amazing. I mean, if you select the moon on Stellarium, and have it centered and selected, and then put it on fast forward, and subtract the Earth's atmosphere and the ground, it rocks and rolls all over the place. It's quite funny.
Let's do that. Yeah, that's good. Good idea. Okay,
so it's constantly, because I image them in quite a lot, and there are features that they only come into view with certain librations. You can't see them. So there's like certain times that are like it's really there's good times and bad times to see things that are like on the limb. And we see about 60% of the lunar surface because of libration. Right, You've probably heard that.
Yeah.
Yeah.
No, thanks for that, John. That was very interesting. Yes, you got me going. I'll go and have to look at that in Stellarium now. That was, Yes, I was aware that the moon was tidally active in some strange way, but as you say, it's probably due to the geologically active and the result of some of these tidal effects. But I think these tidal effects are not. Well, okay, I'll have to go and check on that. But you were saying that you think the tidal effects on the moon are largely due to the elliptical nature of the orbit, whereas I'm thinking it might be due to the fight between the moon and the Earth, and the sun might also be adding to it.
Well, it would. I mean, it's the same. I don't know for certain, but I would make an educated guess that you have the same effect as you do during the equinox tides. So I would imagine that if you have a combination of the elliptical orbit that coincides with with the moon, the Earth, and the sun being in a direct line like they are during the equinoxes, you would get a more pronounced. You would get like the biggest kind of spring tide, if you like, on the moon, just like you do in the Earth.
Right. Okay. You seem. I got the impression earlier you were not in thinking the sun could be the cause of the tidal behaviour of the moon, but it sounds like you are sort of saying that now. Okay, great. Okay.
Oh well, yeah. I mean, but
you had made a good point about the elliptical orbit. That the elliptical orbit is also contributing that. I must admit, which I hadn't really considered. So yeah, that's good. So,
because I mean, during like the first quarter and last quarter, that's as far from the sun and the Earth and the moon being in line. So when you're a new moon or a full moon, regardless of whether it's not at the equinox, you would have quite a good alignment, even if it's not at the equinox. So the sun, in that case, the sun would contribute to it. Yeah, definitely.
Okay. Yes, I hadn't really thought about the elliptical orbit being the cause of the moon's geological activity. But yeah, that's a good one. Yeah. Oh, thanks, Shawn.
It's not a huge amount, the difference between perigee and ecliptic. Well, I suppose it is quite elliptical.
Well, yes, 15%. I mean, the moon changes size by 15%. Although the eccentricity value is quite small and the change is quite small, it actually, it's 15%, which I think is quite chunky, actually.
Yeah, it's 20 odd thousand kilometers difference or something.
Yeah, I don't think people appreciate how far away the moon is. It's only when you do a scale diagram of the damn things you realise how bloody far away that moon is at its normal, 30 odd times the radius, or 60 times the radius, 30 times the diameter. It's a bloody long way away. And then you realise what the Apollo missions had to do. It wasn't just like putting up the ISS, getting out there. It's quite a big difference getting to the moon that is sticking something up in orbit.
So I was having a bit of an argument with surprise, with a flat earther about there was a bit of Apollo hoax stuff going on, and he seemed to think that the command module remained hovering above the Sea of Tranquility the whole time that the LEM was on the surface. And I was trying to explain to him that the command modules constantly in lunar orbit. So I think it was about 2 hours each orbit. And I sort of began to kind of think, because they would go out of radio contact, obviously, on the far side of the moon. Yeah. And Michael Collins, on his own, I had heard it said before that he was the most remote human being in the history of human civilization at that point. And I thought, Christ, he was, wasn't he? I mean, Buzz and Neil Armstrong were together, at least on the lunar surface.
Yes, on the other diameter of the moon closer. Yeah,
but it must. I mean, I find like replays of the Apollo missions. I mean, I'm a bit of a geek, obviously, but I find stuff like the Apollo 11 descent being like edge of the seat stuff. I really do.
Yeah, well, particularly when you hear what the computing thing did, the actual processor became overloaded, and they got some error message just as they're about to land. And then, fortunately, some guy was familiar with the error message and popped and said, "No, you can ignore that." And they said, "Okay, right, we'll carry on going in." And then,
they're counting down how many seconds of fuel they've got left.
Yeah, 15 or 30 seconds they had left. Yes.
Yeah.
It really was edge of the seat stuff, as you say. It really was. They within 15, 20 seconds of having to say, no, sod this, and had a computer problem about 1 minute beforehand that said, no, I've given up, computer's not working, what do I do now? They said you have no idea whether the computer suddenly stopped working. It's come with this error message. And, if I'm using a bloody program, it does that, I stop using it. But if I'm actually heading towards the moon and it comes up with a message, I think I'll be saying abort now.
Well, there is a bit of a misunderstanding about the alarm codes, because it wasn't quite as if the computer was going wrong so much, but it was doing what it was supposed to.
Exactly.
But
they didn't know that. They just, they've never seen this code before. Come up in the middle of this thing, thinking, "Well, has it stopped working? What's going on?" But fortunately, someone who was really familiar with the codes knew that it was just a loading issue. I think it was brought on by the fact they switched on the radar to work out the distance in the final approach. They switched on this radar to check the distance, and that the extra little bit of load on the CPU, because it had some real-time operating system or something like that, or some equivalent operating system, and it was just saying, "I can't service this request."
Yeah.
And then they I don't know what they did to make it not But the point was they got this error message and they were able to. Some clever chap was able to say, "No, you can carry on with that, no problem. Keep on going."
I think it was somebody quite low down in the pay scale. Actually, it's like, "Hey, do you know what this alarm is?" And he was sort of brought into the control.
Fortunately, he was in the command. He was fortunately in the whatever it is, the Houston's mission control, whatever it was, and he was able to immediately say, "No, ignore that. Carry on."
It was a 12:02 alarm. That's how much of a geek I am.
Bloody hell, John! But John, that is. I thought I had some. I was trying to remember the number actually while we were talking about this, and I thought, no, that's ridiculous. You do right, well done.
But there's another. I was quite interested on the Apollo 15 landing as well, because that almost went really badly wrong, because I can't remember what happened, but they overshot and they had to recalculate where they were going to land as they were coming in, and they were quite far off the intended landing zone. And when they landed, one of the legs of the LEM went into a crater, and it was getting close to the point where they were at too much of a tilt to ever actually safely, take off again.
Wow.
And they had, once they landed and they'd gone through the checklist and everything, they're allowed to sleep for a couple of hours, and they woke them up early because the LEM was depressurizing, and they're like, oh shit, and it turned out that one of them had forgotten to close a valve when they went to the toilet. That's all it was. But
Terry, can you check the internal chat?
Anyway.
Sorry,
hello, Peter.
Terry, can you check the internal chat?
Yeah, I did.
Yep. Okay.
I don't know how to do that.
But yeah, it's one of my favorite parts of the moon, the Mount Hadley and the Hadley Rule, and like where Apollo 15 landed.
Right.
Some of the things that you can actually see. You with a decent sized telescope, you can actually see the mountains that are in the pictures of Apollo 15.
Right.
And it's so
you're presumably fully familiar with the picture of the moon showing where all the Apollo landings were then?
Yeah, not all of them, but yeah, I'm quite well acquainted with the surface of the moon.
Right, okay.
It's
I'll defer to you on this area then if I come across it. Yes, I'll definitely bear you in mind.
I do remember once upon a time that when I wasn't quite so much into astronomy when I was younger, and I heard how fascinated Patrick Moore was, Sir Patrick Moore, and he was he was a kind of person who would say you could just spend your whole life just looking at the moon. You don't have to look at anything else. And I thought, well,
because NASA actually employed him as a moon expert. He really was very familiar with the moon.
And I'm not saying that size is everything, but my telescope is bigger than the one that Patrick Moore had in his garden.
Wow. Yes, because his what was his, a 12-inch or
12? Yeah, mine was 14. I haven't actually finished building it yet, but it's been in the pipeline. It's got research grade optics.
Wow.
Which I had to save up for quite a long time.
Wow, John, and you're building it yourself, you say?
Well, it's an old Orion Optics Newtonian, which I'm customizing. I'm changing the focal length. I had the mirror made to my specification, and so I'm turning it into an astrograph, like a photography dedicated telescope. You can still look through it, but it's sort of optimized for photography.
Wow.
But I just got a new camera today, actually, which I'm really excited about.
Oh, John, I'm really impressed. Well done, John. So you've actually got a big project then. So you've acquired them. You've had the mirrors built for you, and the structure. And have you built the structure to put the house of these things in then?
Well, I've got it's an optical tube. It's all kind of there. I need to shorten the optical tube to correspond with the new focal length. It's about 200 millimeters shorter focal length than it was originally.
So, are you doing all this yourself? All this building the structure yourself?
Well, yeah. Well, yeah.
Well done, John. That's impressive.
But it's I suppose I don't
steel?
think
Is this metalwork you're using?
Well, it's aluminium. It's an aluminium tube. It'll be carbon fiber at some point, but it's another £1,000 that I can't really justify.
Yeah.
It'll have to come in the dead of night, and the missus will say, "What's that?" I've always had that. It's always been there.
Just in the basement.
But it's because I'm really interested in very high magnification stuff, and focus is a real issue with a metal tube because of the expansion and contraction of metal with temperature.
Right.
So you're effectively you get a change in your focal length if the temperature changes.
Yeah.
And carbon fiber doesn't do that. So that's and it looks really sexy. Obviously. But yeah, I got a camera today. I've been waiting for it for ages. It's a cooled CMOS camera. It goes down to minus 30 Celsius ish. So if you're doing long exposures, there is no read noise from the infrared heat of the camera itself. That's why it's cooled, which is very handy.
So you're doing all this metal work. You're an engineer, are you? You can do this all precisely and cut and do stuff without anything,
No. Well, I mean, I'm not. I'm quite a handy guy. I mean, it's not my background. But I'm one of those people that I can sort of turn my hand to most things.
Okay, well, I always respect an engineer, people who can build things. When I have a go at it, I can build. I build often a workbench and things. I build stuff. I've never built anything on the scale of a bloody telescope. Bloody hell! Okay,
but it's not. I mean, I would be very, very impressed by people who actually grind their own mirrors.
Yes.
Which is. But this to get a research grade mirror. It's got to really be done by a computer, and it's certainly got to be analysed with an interferometer to gauge the quality of the surface.
Right.
But it's but the mirrors. I can't remember. I think it cost $2,500. Wow. I've had it for a couple of years, but the quality of the mirror is gauged by the maximum peak to trough of any imperfection on the surface of the mirror.
And it's a circular thing, presumably.
Yeah, it's a circular
mirror.
Parabolic.
It's a parabolic mirror.
Parabolic mirror, yeah.
It's a parabolic mirror, right? Okay, yeah. That's the trouble. It's doing the parabolic bit that's the tricky, isn't it? There's no easy way of doing that. Building something parabolic.
But the quality, the smoothness of the mirror is measured relative to the wavelength of visible light.
Wow.
So it's called a 1/10 PV mirror, which is 1/10 peak to valley. So at say, I think it's 550 nanometers. It is 1/10 of 550 nanometers. So it's the mass. Basically the peak to trough is a maximum of 50 nanometers imperfection.
Oh my God! So it's smaller than the wavelength of that typical wavelength of 550 nanometers, things like green. So in other words, I can't quite cope with this. You're telling me that your mirror is so close to being parabolic, it was within 1/10 of the wavelength of green light.
Yes.
Jesus Christ. That's amazing.
But it's
that is absolutely amazing.
But I think they go. They do go further.
Are you sure about that, Alan? Are you sure? Sorry, John. Are you sure about that? That's just beyond belief.
Yeah.
I mean, that's incredible. Within a wave. That's amazing.
So so if you get the optics up to that quality, what it means is that you got what you call diffraction limited optics.
Right.
So the image that you can record, the quality of it isn't limited by the telescope or the optics. It's actually just limited by the nature of light. itself.
So the Rayleigh criteria kicks in there. So you could teach some flat earthers about that. Yeah, the Rayleigh criterion, right? Okay.
How does that compare to a normal lens, like one that you buy at Walmart as far as PV?
I think you would get a sort of standard telescope, like Celestron or something like that. They'd probably be somewhere between 1/4 or 1/6 PV, something like that, which is pretty good. But it's the difference. It's like the difference between the standard kit lens that you get with a DSLR camera and actually spending a lot of money on a decent one.
Right.
You know. But yeah, it's but there's loads of links in the chain, and I've got a 10-inch telescope that I use a lot. So I'm just trying not to be rushed and making sure that every single thing is done properly. So it should be a really high quality instrument when it's finished.
Can I?
I wasn't familiar enough. I wasn't familiar enough with telescope technology to know that's the resolution they've got, even a dodgy one. But right, I wasn't aware. Yes, I really must get myself a telescope. That is just absolutely amazing.
Just one thing I was going to say before I forget: the fuck up with Hubble.
Yeah.
When they put it in orbit and there was a problem with the optics.
The mirror was too flat, wasn't it?
Yeah, well, I in like astronomy observatory circles, the story goes that
a bit of dust or something got somewhere.
No. It was the Hubble technology was derived from a spy satellite project called Keystone. So there's about 20 Hubble type satellites in orbit, but they're pointing at the Earth, not the other way around.
Yeah.
And at the last stage, the Hubble guys, the techs were sort of like, can we use your equipment to measure the quality of the mirror? And U.S. Department of Defense just said, no, we're not going to give you everything. You know, we don't want you to have a sophisticated an instrument as we have. And that was a big part of the reason why there was such a problem with the mirror. But they corrected it. But because of that, Hubble is
only
not
in space.
yeah, and it was a very impressive mission. But because of that, Hubble is not a diffraction limited telescope. It is actually operating at a lower resolution than it could.
Yeah.
So it should have a resolution of 0.05 arc seconds, but it's actually got a resolution of 0.1 arc seconds. But it's still an amazing piece of kit.
The second value you just gave was smaller than the first one.
0.05 arc seconds should be the resolution, but the actual resolution is 0.1.
Oh, okay, so it's half the resolution it could be. Okay, right.
And the resolution of my telescope in ultraviolet, surprisingly, is 0.22 arc seconds. If I really tune it to within an inch of its life.
So that's you're telling me that your telescope has only half the resolution of the Hubble in ultraviolet.
Yeah, but it's a big difference. It's not. I mean, if we say 0.1 versus 0.22, it doesn't sound like very much, but that's quite a big difference. And as well, Hubble's 2.4 meters wide.
Yeah, you can't see dark images. Yeah, I mean, obviously you're limited by the amount of light. Yes, but nonetheless, you're telling me at the ultraviolet wavelength, yours has only half the twice. So in other words, yes, has half the resolution. In other words, twice the angle that it can resolve.
Yeah, but in the middle of the visual spectrum, it's about 0.3, 0.33.
Right.
But doesn't that make a big difference? Isn't that like the inverse square law, where it doesn't sound a lot, but it's proportionately a lot more, isn't it?
Yeah, yeah.
I mean, factor of 3. It means that in other words, he can see something. Hubble can see something that's a third the size of the thing that he can see, which I think is an amazing ratio. That's what he's saying. That's what he's saying. I think.
Yeah, I mean, if you take the example of craters on the moon,
yes,
I could see down to a third of a mile a diameter crater, and Hubble could see down to 1/10 of a mile diameter crater.
Yeah, so
doesn't sound a big difference, does it?
No, it doesn't. No, that's the point I'm making. That's why I'm going.
Well, but I mean,
it doesn't sound a big difference. That's a bit.
But the other, I mean, even a say you've got a 100 mil diameter telescope, which is it's quite a common size for a starter telescope, for like 4 inches diameter. That'll have an angular resolution of about 1 arc second. So Hubble is only 10 times the resolution of that telescope. So once
it's the light gathering, I suppose, is the important thing. The point is it can see very dim things much further away than you can. It's not so much the size resolution; it's the light gathering ability that really gives it the edge.
Well, it's in space, isn't it? I suppose it's not got the atmosphere in the way. Yeah.
Well, there are various techniques to minimize atmospheric interference.
It's correction art, which amazes me.
But
mirror wiggling.
Well, there's a thing that I use called lucky imaging, which basically means that instead of taking a long exposure, you're taking many, like thousands, of short exposures, and then you get software to evaluate those exposures for quality, and you throw away maybe as much as 90% of them. But a fraction of them will be taken in those rare moments when the atmosphere just conspires to give you a really clear view, and you only keep those ones, and you stack them together.
That's an interesting idea. Yeah,
that's the way I thought it should have worked. It's only when I found out a decade ago how these things actually work, and they actually manipulate the mirrors to compensate for in real time. I thought, what an incredible idea to come on. I was thinking much more along the lines of the system you just described. The idea of having some real-time correction to these things by actually wiggling mirrors, I find absolutely amazing. This can work. I mean, it's just unbelievable.
If I become a bit more well-heeled, there is actually a piece of kit which is, I can't remember how much it is. It's maybe like £5,000 or something.
That's what it's called. Wiggly mirrors thing cost. Yeah, £5,000. That's about that, right?
It's called active optics rather than adaptive optics. So you've got a tip tilt prism, which senses the turbulence of the atmosphere in real time and redirects the image onto the center of the camera sensor.
Right. That's so it's not. So adaptive optics is wiggling the mirror, and active optics is wiggling a prism.
Yeah. Right. Yeah. But it's a lot of money. And even then, you're still, you can take long exposures, but if you get a period of particularly bad seeing during that 5 or 10 minutes or whatever it is, then it's still going to affect it. But if you use lucky imaging, you can just make a long exposure out of lots of short ones and throw away the ones that are not very good.
Yeah. What amazes me is the time that astronomers and like these people I've been looking at, the LRI people and all these various bodies of people, time, effort and human energy and observations that they've put in over, I don't know, 50, 60, maybe 100 years for astronomy, maybe more for astronomy actually. And that data has been collected and collated, and we've just pushed back the boundaries of finding various things out. Yeah, even very small things by doing lots of experiments like these photo multipliers that they put better ones in the thing I'm talking about, this laser bouncing up the moon, and they've improved the precision, and then they've compensated for all these phenomena that they see, right, like tidal crusting and this, that, and the other. And then it amazes me when you get the hand waves from sort of flat earthers who dismiss that. And I find it quite objectionable because you're waving away so much human endeavor. Like I heard Spurs this morning, right, on the show saying, oh, well, all these scientists have actually wasted their lives. Isn't it a shame that they've completely wasted their lives by believing in things that are fake and that don't exist and that's, a load of nonsense, yeah? And he was talking to a young chemistry student, I think it was, or something like that, and saying, why are you even bothering going to university and doing your PhD and your research? Because it's all just fake and it's all a load of rubbish and you're going to waste your life, yeah? And I find that quite objectionable because, none of those people have really assessed or even looked at that deep data. Fair enough, you could argue with it and say it isn't real and so forth, but you should first of all engage with it, look at it, because when you start to research any of these areas, and I wasn't really knew about these kind of astronomical observations, the amount of effort and precision that people put in, it isn't just made up stuff at all. These are real endeavors, done by real people.
I mean, it's as you can imagine, for me personally, having been involved with Royal Observatory and what have you, I find it really, really offensive. It really gets to me, and it's and not just astronomy, but if you've ever worked at an observatory and met engineers that work on this kind of stuff. I mean, the holes that Apollo hoax theorists try to poke in the Apollo program, it's laughable.
This is what I mean. It is laughable because what you're doing is you're downgrading someone's expertise. So I've worked in CERN. I worked in CERN before, and I've also worked quite a lot with GPS and satellites. Yeah, certainly with the signals from them. Yeah, and as you say, the amount of endeavor and thought and people's whole careers, right, that go into actually quite small, pushing the boundary just a little bit forward, right? People are not doing that for fun, and these are very clever people who would very, very quickly realize that something wasn't right. Yeah.
But the point I was sort of trying to make is that when people say, "Oh, we couldn't have gone to the moon because of this or because of that," there's such piffling, stupid little problems compared to the actual challenges that had to be overcome. It's just a joke. I mean, it's I've in the Saturn V alone, Christ, the amount of sheer sort of bloody mindedness and trial and error to get that thing to work was astonishing. But I'm actually in my what's going to be my observatory. I'll show you this.
All right.
That'd be great. Look forward to that. That'd be fantastic. Are you building a new one then, John? I mean, by the way, I don't know what your background is. I've obviously not been on the show where you've spoken about your astro. I thought you were like a guy that rescued people from the sea for some reason. Maybe it was your picture, your icon.
I was. Can you see my I don't
finger?
Know how to do that.
We can see your finger.
There we go.
I can see the word instrument.
So that's where are we? Yeah, so that's the focuser of the telescope. I'll just I'll back off a bit so you can kind of.
And by the focuser, is that like a little thing that you look through to line it up, or that moves the whole thing up?
That changes the focal length. So.
Did you build a special shed for it?
Well, this is going to be the observatory. So you change the. That's where let's loosen that off. So you see the barrel coming in and out.
Yeah.
And it's got a 10-to-1 fine focus. So you're changing the focal length of the.
Sorry, what's that wiggling backwards and forwards? What's this thing that's coming in and out?
That's the barrel of the focuser. So the camera would be on here.
Right.
You focus it by.
Right. The camera would be on there. Right. Okay. Yep.
But this is just this bit.
Yeah.
The focuser cost about 450 quid. Ooh. It's a Rolls Royce focuser. It's beautiful.
I look at it there. Look at the smooth action on it. I can see just as I do a lot of mechanical stuff. I can see just from you twiddling it. Look at that. So smooth, isn't it? It's super smooth. I don't know what kind of gearing they've got on it. I mean, it's just incredible.
But that's where is it there? There. So that's a 10-to-1.
Yeah, nice action. Look at that.
And so eventually I'll get an electronic focuser because you can't. That's the mount as well.
And that weight there, is that to counterweight the actual lenses? Is it that? It looked like some weights on the bottom you had there.
Yeah, well, that's the counterweights for the weight of the telescope. Yeah, and there's not. I don't have enough. Actually, I need to get some.
You don't have enough. Right. Have you ever used that telescope, John, or is that a brand new entry to the John Watson?
No, I've had it for a long time. It used to be a what you call a Dobsonian telescope, which is that's just it's really the mount. You've got an alt azimuth basic mount that that's what it was originally. I've converted it to work on an equatorial mount. I mean, you can't really easily do astrophotography on a alt-az mount because of the movement, the apparent movement of the sky.
Is an equatorial mount driven by electronics and computers?
Oh yeah, well,
always, yeah, because it has to work out what the movement is. Yeah, is that right?
Well, no. You just align the axis, and then it just moves at a particular rate. It doesn't have to be complicated.
Once you've got really? So they're ones that are just mechanical, then, aren't they?
You do get I've got another. I'm sorry about the quality of this video. It's a bit crappy. I don't have a light in here.
It's
but where are we? Can you see?
Yep.
Oh yeah. That's I made this drive. See the cogs.
It can be just mechanical. In other words, Toady.
Yeah.
They usually were used to be clockwork, weren't they?
They used to be.
But the first thing, that big white mount. The first, it cost. I think it cost about £1,200 or something. But the first thing I did to it was I took it to bits before I'd even used it, because there was an upgrade for it made by an engineering company where you could change out the gears for belt and pulley, which made it a lot smoother. So my family went away for the weekend, and I had this brand new mount in bits on the same room floor. And I did at one point. I thought, John, what have you done?
Oh, you've gone too far, John. There's too much here. It's all in bits. It's all spread out. Will you ever get it back together again in the right order?
But I did, and it is pretty smooth. But it's I've got a for astrophotography, you can't depend on the mount to know sufficiently where it is and to keep track. So you use an off-axis guider. So you steal some of the light that's going into the camera through a prism and direct it up into another little camera, which is connected to software, and you basically choose a guide star, and the computer sends minute constant commands to the mount to keep the star in the crosshairs. Wow, that sounds amazing. So it's if you can see, that's an off-axis guider. So that's for a DSLR. That's a camera bayonet for a DSLR. That end closest to the camera fits on the telescope, and the guide scope goes in there.
But it actually steals light from your main image. Why couldn't you just not have another telescope along the side that does the tracking, as it were, so you don't lose any light?
Well, you get flexure. You can do that. Lots of people do that. But you see the little prism there? So that's directing light up to the guide camera.
This other little guide camera, yeah.
Yeah. So you can piggyback a little telescope, but because it's not the same optical train, you can get problems. But it's.
And how about those guys where you can go online on my computer screen and I can go in and sort of see live feeds from the telescopes and even put in orders, say I'd like to see this bit of the sky, and sometimes if enough people say they want to see,
I've never done that. Well, no, I have, but if you don't have your own gear, you can actually. I mean, that's what professional astronomers do. I mean, there's no.
Yeah, they do crowd share, don't they? As it were, or whatever, with big observatories.
Yeah, but there's no. As far as I know, there's no functioning research telescopes in the UK anymore. They send a request to the Atacama Desert. And in fact, the funny thing is, I used to get asked by the observatory to come and set up telescopes for them because no one knew how to do it.
Oh, really?
About 150 staff at the observatory, and no one actually knew how to set up an equatorial telescope. because they would literally just request images and it would just come back over email, and they never went anywhere near a telescope, which is kind of odd. Made me feel very useful.
Yeah, well done, John.
But
who was this? Who was this making the request?
What the Royal Observatory
in London?
No, in Edinburgh.
Oh, no, right.
At the time, yeah.
Right.
But yeah, I haven't been involved with that community for a couple of years. I've moved north to darker skies. But yeah, it's
well done, John. I'm impressed.
It's a huge
endeavor.
Yeah, I mean it's a lot of expense, but I've that telescope, and I've been getting the parts for it for a couple of years, so it's a lot of money, but spread over quite a long time.
So you haven't actually done any observations with it yet?
Oh no, I have used it. I have used it in its original state from Edinburgh, and it's quite a nice instrument as it was, but not. Yeah, it needed pimped.
This is the trouble, right? It's like all meddlers. It's like me buying my lathes and my machine tools and my milling machines, right? I spend more time upgrading them and doing little bits and pieces, right, to make them a better tool than actually doing any real engineering with them. It's kind of, it's always a hazard, isn't it, of men and gadgets, I think, yeah? A bit like cars and motorbikes or any of that kind of stuff, right, where,
I remember I was a prolific treehouse builder when I was young, and then once it's finished, you're like, I suppose I better build another one.
Yeah, exactly.
What do you mean when it's finished? No such thing.
Well, yeah. Well, I'd either think, oh, I need to build another one, then, or I'd start planning the extension, which happened quite a few times. One of my old tree houses is still there. Actually, I've come back to where I originally came from. And
what you mean? You moved back home and.
Well, just
back home or just in the same village?
Oh, just the area. It's where I grew up, and there's one of my tree houses that you can actually see from the main road that I built 30 odd years ago. It's still there. It's got a felt roof and glass windows.
Oh, really? As a 10-year-old, you have been quite adventurous then. Did you get an adult?
Well, there was a lorry, like a truck scrapyard next door. And so it's got lorry, like Arctic windows.
Oh wow!
And it's got a carpet actually as well.
Say hello.
So, but yeah, I'm going to try and get this new camera up and running tonight.
Oh, what camera have you bought? What have you got?
It's called hang on.
Has Alan got to butt in a minute before because you wanted to announce something?
It's
Alan's not. Is it Alan dropped off? Yeah.
Oh.
It's called a ZWO 290.
That's a camera?
Yeah.
It's like a mini computer or something. Camera?
So it's got a 2/3 of it.
Yeah.
2/3 of it is a cooling sink.
Right.
So the bit that I'm holding basically is the camera.
Well,
and
why
the rest
would it get
of
that hot then, John? Explain to me what's going on there. That looks incredible. I've never seen anything like that. Doesn't even look like a camera to me. So what's going on?
It's
a Peltier cooler.
So it's, I don't know if you can see the sensor there.
All right. Okay. Oh yeah. Wow. I can.
So it's a really small sensor.
There's no optics train on it, right? That is literally just the sensor, is it?
Yeah. So the reason why it's cooled, you can get them without cooling.
Yeah.
What happened?
He dropped, sadly. He must have Pretty interesting, that camera. I've never seen a camera like it.
Yeah, I like anything to do with optics and
I know, it's
telescopes
fantastic looking
and
at it. Yeah.
equatorial mounts and
it's amazing stuff, isn't it?
I haven't got a clue about how they really work properly, but I like to know what I can.
Nor me, but they're always so fascinating that you can kind of get light, and do more with it. Just always seems amazing to me, like magic.
But the reason for the cooling is that if you're doing a long exposure, you do get. I'm talking like 5, 10, maybe even 20-minute long exposures. You get infrared photons just from the mild background heat of the camera, which end up on the image. And you can get rid of that in processing. You basically put the lens cap on and take the same exposure,
and then you know what the heat signature is, and you deduct that.
Yeah, but that's if you're doing 20-minute long exposures, that's a real pain in the arse. If you've got do it again with the
lens cap on. Yeah.
Alan, if you had.
Alan's back now. You were going to say something, Alan?
Yeah, waiting for Alan to butt in.
Yeah, sorry. I would like to apologise to Rumpus again for earlier. Rosie had just come home and she'd been at the hospital all day with her. One of the things she had at the hospital today was her 20-week scan.
Oh.
For those of you who know, that means that she found out some information.
Yes, exciting information, hopefully.
I shall be having a grandson.
Congratulations.
Oh, congratulations.
Not two. It wasn't twins.
It's not twins. No, we knew that already, but it's...
I remember it being called hot dog or hamburger. Did they say that to you?
I don't know. I wasn't there. It's not... I'm granddad this time around, not dad.
Does Nathan
better. So it's even better. Yeah, well, Nathan had to go to work today because he got a.
Oh, we're going to do the usual pink or blue type hint for him when he gets home.
Rosie's already. Although he couldn't do the, although he couldn't be there, they let Rosie FaceTime him while they were doing the scan. While they were doing that bit of the scan.
Oh, okay.
Yeah, you can never tell yourself, can you? I always looked at the scan and I still couldn't tell. You need the experts to tell you.
Yeah, is it a boy or a girl? You tell me.
Yeah, exactly.
They got my son wrong.
Yeah, they do. They did say to her that it's only 99.9%.
So they do get it wrong, don't they? Occasionally.
Yeah, my son was told he, I guess, had a hamburger. Is that what you're using terms? He didn't have a hot dog.
I could tell my son was a boy on the ultrasound. He had good genes. Couldn't resist.
Yeah. So that was the problem. Rosie had come home from the hospital and was trying to tell me that, and that was what was going on. So that's my excuse for cocking that part of the thing up and muting Rumpus, because I hadn't realised I was muted myself because nobody would listen to me, and I was getting Rosie wanting to talk to me, and and seeing that there was some issues going with the stream, and it just got a little bit. And actually, it's a good job Terry took over, because, as I say, we just had a power cut as well, so that would have killed everything. And I saw you. At least I did get to just see your telescopes and stuff, John. I am very jealous because I like those types of toys.
I've just put it together just to show you kind of how it. Can you see
what's that we're looking at? I can't see the white thing anymore. Is this a different thing, John?
Well, that's This is my second biggest telescope.
Your second biggest. You've got several of them.
I've got loads of the fuckers.
Right.
This is a 10-inch.
So size doesn't matter.
Hang on, 10-inch. Is that the length or the width?
That's the diameter of the optics.
Okay, so when I hear these things like 2.4 or 24 millimeter or something like that, how does that relate to this 10-inch?
Oh, it's totally different for camera lenses. If you've got a 20 mil, it works
in a completely different way. Is it the two don't ever near the 20 shall meet? Yeah.
Yeah, I mean, you don't really describe a telescope by the focal length. You describe it by the diameter of the optics.
Right. Okay.
So this telescope has a 2,500 millimeter focal length.
So it's 25 centimeters.
Yeah, but it's no, so 2.5 meters.
2.5 meters. Hey?
Yeah,
it's not 2.5 meter long. Is it?
No, but it's got a. Well, I suppose you could say it's got an effective focal length of 2.5 meters, because the light goes in, bounces off the primary mirror, back down off the secondary mirror, and out again. But before it even goes in, the corrector plate, which increases the focal length.
Quick question there that I've never really understood. How can you get a decent image when you've got a hole in the middle of the mirror that you're bouncing the image off of?
I've never understood that either.
Yeah, you know what I mean? You've got this mirror, haven't you? It's a bent mirror, but the middle is missing, isn't it? Because that's how it works in these reflector telescopes, yeah?
Yeah.
Yeah, but it doesn't. Well, in this kind, it doesn't. It doesn't make any difference. It does the size of the obstruction, which all reflectors have, makes a difference. It reduces the contrast depending on how big or small the secondary mirror is. But it does. You don't end up with a sort of holy image or anything.
How can that be though? How does it not? How do you not end up with a holy image, as it were?
Well, you're so far the hole in the mirror and the secondary mirror are so far from the actual point of focus that it just doesn't make any difference. If you could draw the focus far enough, you would see a hole.
It's the same reason why you zoom in with a camera and you put one of your fingers in front of it. You see.
Yeah.
Like you said, it depends on where the focus is.
Because I could be shooting underneath a big thick like telegraph cable, and with it running right through the middle of the image. But it's so far from what I'm actually focused on that I can't see it at all.
Wow.
So, but yeah, so that's. I just thought I'd show the. So that's how the.
Pretty cool, man.
I better shill Alan's thing too while I'm here. I'll let the outside see it. I don't know if I can share it in here.
So that's the.
What's that other one you've got? That's a camera, and what's that other red one?
That's the guide camera, and that's the imaging camera.
Okay, and how much is one of them roughly? One of those cameras?
But the imaging one.
Yeah.
I got quite a hefty discount, but I think the RRP's 600, 700.
Okay, so they're quite expensive, moderately expensive. Okay, I mean,
but it's not a. There are much more expensive cameras in their range. But
how many megapixels would it be, or do they not talk in those kind of terms either?
Well, in terms of megapixels, it's HD, but the reason I got that particular camera was because the pixels are 2.9 microns, opposed to like a DSLR, which would be maybe 6 microns. And the effect that has is that rather than using a multiplier to effectively increase the focal length and increase the size of the image, the pixels are so small that you can operate at the native low focal ratio without any multiplication or any extra magnification, and get the full resolution of the telescope. So every time you multiply the focal length, you're increasing the focal ratio.
So if you've got a nice, with that, the big white telescope will have a native focal ratio of f4.
Mm-hmm.
So which means the diameter of the mirror is a quarter of the focal length. And the shorter or the smaller the focal ratio, the brighter the image is. So the shorter your exposures have to be. So if you multiply the focal length or extend the focal length, the image will get darker and darker. So I've got that camera. Basically, I got that camera because it's got small pixels. I don't have to go to a higher f ratio, and I can still shoot at a fast f ratio and get decent images. I've probably not explained that very well, but
I need to look up what the f things are. I never understood f-stop, so I do need to probably go back and reread optics a bit to understand them properly, because it is something that I'm now starting to dip my toes into, so I probably should understand
it's similar. I can probably get the big telescope down to f2.8,
mm-hmm.
which is the lowest, really, the smallest f ratio that you can really go to before you get aberrations that you can't really correct. It's basically, it's even the same with camera lenses. The smaller the f ratio, the more light you're getting in, and the brighter the image is. So you want to keep it as small as possible, particularly for photographing.
For obviously photographing dark things, yeah.
Yeah, I mean, like nebula and galaxies and what have you. And it doesn't matter at all if you're looking at Jupiter, say, because it's so bright. You could take it up to f30, maybe, and really zoom in.
What's the best?
All right, let's cut to the chase. Do you have any images of the work that you've done?
That's what I was just about to ask. That's exactly what I was going to ask. What pictures have you taken?
I've got a Flickr page, but they're not particularly. There's a sort of mix of like small telescope stuff and landscape stuff. I can probably post a link in the chat somehow or other. But yeah, I've done the last while. I've been doing a lot of like landscape Milky Way stuff, with a view to building a portfolio with.
What does landscape mean? It means it's got a silhouette of some trees and stuff, and then you see the stars, or what's the landscape mean? Sorry.
It's just what I call. I mean, you know, you heard of Colin Pryor, photographer Colin Pryor.
No, I can look him up though.
But it's basically a photogenic landscape, but shot at night with hopefully the Milky Way in the sky
in the background. Oh, right, so it is the kind of thing I'm imagining. Yeah. Okay.
Yeah. But which is very difficult to do.
I've seen some amazing ones in Africa, I think, where they're out in the bush or whatever. You see what I mean? And they've got the landscape, and some trees and stuff, and then they've got the sky, and it's so bright. Amazing.
It's but the thing with doing it here is the weather windows are few and far between, and you got to just be ready to go.
All right, his stuff is proper landscape. Colin Pryor, the pictures I'm looking at, there's no stars there. It's John. It looks like there's some amazing things he's done in Antarctica and places.
But yeah, I mean, just in terms of the actual landscape part, the hope is to get sort of iconic views of the Highlands, similar to that kind of stuff, but shot at night.
With the stars as well, because so that telescope you can't look at the landscape. Then it's not a landscape telescope.
Oh no.
It's a stellar one. Yeah,
it's that stuff is done with a 14 or 24 mil camera lens, DSLR, but still with an equatorial mount.
It's a question: do people actually buy a normal DSLR, SLR or whatever, and attach it, or do they always buy those cameras like that red thing that you've got?
Well, I've got a Canon 6D, which I'll be attaching to the telescope for large like wider field stuff. Those red cameras, both of them have got really quite a small field of view. That's just because of my interest in how small a thing can I actually see. One of the targets on my hit list actually is the Einstein Cross. Have you ever heard of that?
No, what's that?
It's a gravitationally lensed quasar. I think it was one of the first evidences of gravitational lensing, which unfortunately happened after Einstein died. But it's one quasar which is lensed into 4 points of light by a galaxy that's in between us and the quasar.
And the quasar.
They call it the Einstein Cross because it's the 4 points of a cross. And I know it's the same quasar because if you analyze the light of each point, it's got exactly the same spectrum.
All right, so it isn't 4 things; it is exactly the same spectrum. Yeah.
Yeah. But it's very small. It's like right on the edge of what's possible. So yeah, it might take several attempts.
Is there any excitement up in astronomy? Is there still things to discover? I don't know, comets or other stellar objects that maybe is there anything yet to? Is there still stuff to find? I guess.
Planet 9 is this year has been.
Nibiru? Is that what you mean?
Well, for a couple of years, there's been strong suspicions. More than suspicions that there is another planet beyond Neptune.
I thought that was called Pluto when I was at school.
Beyond Pluto.
Is Pluto still a planet, or has it been downgraded again? I can't remember.
It's been promoted sideways to the king of the dwarf planets.
Ah, okay. So how many planets are there? 8 or 9 in the solar system?
8. 8 major planets. So, but way beyond the orbit of Pluto, there is thought to be another planet because of the perturbations of the orbits of other objects in the Kuiper belt, which is the way they found Neptune in the first place, because of the orbit of Uranus. But they've been steadily building.
Really? Can you not see Neptune? You can't see Neptune then. That's not one you can see.
You can see it.
My stellarium says Neptune's on there.
Yeah, it's such a small point of light, and it's got such a slow orbit that
you can't tell it's not a star. I see. Okay,
once they knew where to look. Then,
No. What I meant was, I thought the word planet came from wandering stars. So the way they knew they were planets is basically they moved a lot more than stars. The ancients, when they were just looking up at the sky. Yeah,
but the further out from the sun, the slower the orbit, or the longer it takes. So if you do it's the way they found Pluto and presumably Neptune, is you do a blink comparison. So you take a shot of the area you think it might be, and then a week later or 2 weeks later you take another image and you do a comparison, like switch between the 2 images.
John, can I ask a quick rhetorical question?
Yeah.
If lenses,
rhetorical questions.
if lenses have to be spherical, how can an Einstein cross be caused by gravitational lensing?
I've never thought about that. To be honest, I don't know. I don't know. Because you get the type of lensing that you see is like a sort of a.
Yeah, if the lensing is uniform and if it's spherical, you get an Einstein ring, partial or complete, right?
Yeah. So I don't think I've ever actually read about what they think's happening with the Einstein cross. It may be one of these things that I've read and has leaked out of my ear during my sleep. but I don't think I've actually read into it. I'll have to do it now.
Yeah. So I'm just throwing it in there as an argument for irregular lens.
Yeah, because I think it's a galaxy. Well, it must be a galaxy that's in between us and the quasar. Yeah, I'll have to look into that. Because all I've done really is sort of crunch the numbers to see whether or not it's possible to actually image it. The separation of the points of light is quite a lot less than 1 arc second. It'd be really difficult to do it. An amateur's never done it, actually.
Really?
Yeah. So
you may not be able to. What's this 1 arc second as well? Could someone explain that simply to me? So here it is.
Well, 1 degree's got 60 arc minutes. 1 arc minute's got 60 arc seconds.
1 degree's got 60 arc minutes. 1 arc minute's got 60 seconds. Is that what you just said?
So an arc second is there's 3,600 arc seconds in 1 degree.
3,000 arc seconds in 1 degree. Okay, and why are they relevant to telescopes? Is that the angle that you're pointing at then?
No, that's a measure of angular diameter.
Size.
Say that again. It's a
angular diameter. So the sun and the moon they're half a degree wide. They're 30 arc minutes wide, roughly.
Right. 30 arc minutes wide. Okay.
32.
Right. But sure, it depends on the distance, does it not?
Yeah. The sun and the moon do well. The sun during the year changes angular diameter slightly, and the moon through its monthly orbit
so
changes.
You can tell my next question. Why is it a good way of? Why do astronomers use it? Why is it a good way of talking about astronomical objects to say, oh, it's I don't know, whatever 1 arc second or 2 arc seconds or something?
That's how big they are in the sky. Like you imagine Earth's sky as a full sphere of 360 degrees around your eyes.
Okay, right. Okay, there. Okay. Okay, I got it.
So it's
right. So Jupiter would be what?
40 arc seconds.
Yeah.
Yeah. Saturn is something like 1 arc second.
Oh, no, Saturn's bigger than that. Saturn's maybe like 30 arc seconds. Jupiter's moons are about 1 arc second.
Mars?
That depends. Because Mars varies greatly in size depending on its orbit.
Actually, I wanted to say 1 arc minute, not 1 arc second.
Mars was the closest it's ever been there a few years ago, wasn't it?
Yeah. There was. I mean, you can see the polar ice caps on Mars, even with an average kind of telescope.
So I was hoping to take, getting some. They're talking about Mars the other day, right? I know it's half the thing of the Earth, but I just had the idea there might be a way of finding no atmospheric refraction effects on Mars because there's very little atmosphere there. But I was assured that unfortunately the rovers are too low down. Because I was thinking, could we look for a horizon effect on Mars? Yeah, because on the Earth we always get into this. There's wavy lines. There's refraction.
Well,
yeah.
Off the top of my head, I think Mars, the atmosphere of Mars is about 1% of the density of Earth's atmosphere.
There you go. So if there is a camera there, or if the rover was in a position, you might be able to see a horizon and prove to flat earthers that the horizon is a real thing.
But it's just a luminary.
Yeah, I know it's just a luminary. Yeah, that's right.
But it's difficult for me to. We were talking about it before to engage with flat earthers about astronomy because it's the sort of depth of knowledge I have of it. It's got to be taken so right back to just really, 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 really basic levels, and they just say, no, that's not. I don't believe you, and I'm just thinking, you fucking arsehole.
What are they?
So it looks like you've still got. It looks like you've still got some light in the sky there, John. Right? It's absolutely pitch black here. I'm looking out at the sky, right, and it's pitch black here. It looks like you still got a little bit of blue. Yeah. Or is that just the?
Yeah, well,
so you're north. You see, you've got another 8-9 minutes from London. Yeah.
Yeah, I mean, we only started to get proper astronomical twilight here in the middle of September. It doesn't get properly dark for about 3 months.
Really?
Yeah.
Wow.
Yeah.
And I'll be getting twilight in another another 3/4 of an hour probably.
Where are you located? Who was that talking?
Terry.
And where are you? No, but you're in Australia.
Yeah, I'm on the east coast, but it's 20 to 5 here, and we'll be getting what do you call it? Astronomical twilight, whatever you call it, for sunrise.
Yeah.
Oh, for sunrise.
2 hours before. 2 hours after sunset and 2 hours before dawn. That's when
so
the
you'll be getting it before dawn, right? Okay. I was just thinking, how can it be? How can somebody going down here? Oh, you had me worried for a sec.
I'm trying to wrap my head around it. How's it been like sunset there, and then now it's going to be dawn here in a little while?
Because you're nearly 180 degrees around the planet.
Yeah, but he had me worried the way he said it. Astronomical twilight, he said, didn't he? So I was panicking there. I think we've got a flat Earth in our midst. Yeah.
No, I could never be a flat Earther. I don't know enough. Oh, wait a minute. That's not right. I think I asked that up.
It seems like it's that way, doesn't it? But, the more you think you know, the less you actually know.
Well, exactly.
But yeah, it's But yeah, I've been examining the stellarium for likely targets the last while. So hopefully I'll get this. I've never used the guide camera. Well, I've never used a guide camera as a guide camera before, and it can be a bit tricky to set up with the computer and physically to set it up. So I shall try to remain calm. You've got to be pretty stoic if you're trying to take pictures of the sky in Scotland anyway. So,
well, the weather, yeah.
Are you able to take pictures of that nebula that they show pictures of, or do you need a bigger telescope for those type of things? Is that nebula that's out there? I don't know about what's out in space, but I know that there's a nebula of some sort they always take photos of that you see.
The Horsehead.
Yeah, that might be it. The Horsehead one, yeah.
The Horsehead's pretty big.
Okay.
Yeah, well, it's if I put the DSLR on the back of that, can you see it? Where's it gone? Wherever it's gone. The back of either of the telescopes, the Horsehead would be and the Flame Nebula would fill the frame.
Wow!
It's
and
just
how far away are they in comparison to other astronomical places?
Well, they're a few hundred light years away. They're near the if upside down from my point of view in Australia, there would be. It's next to the furthest right-hand star of Orion's belt in Australia, and in the UK, the Horsehead is underneath the left-hand star of Orion's belt.
Of Orion's belt. Okay, let me find that Horsehead one. I'm looking for the one that I see all the time.
That wouldn't
work. Nebula, but I can't find it at the moment. It's near the moon normally in the evening.
I don't think that'd work on a flat Earth. Trying to work that out.
No.
If I got it right, nebulae are actually, most of them are quite large across the sky. They're just too faint to be seen. It's not a matter of
you can see
magnification. It's a matter of illumination, literally. Something like Andromeda is something like 2 or 3 times size of the moon.
6
times the size of the moon. Yeah.
But you can see the core of Andromeda. But one nebula that you can see with the naked eye is the Orion Nebula, which is like in the northern hemisphere below Orion's belt. You've got Orion's sword, which looks like 3 stars. And in Australia, it would
that
be
thing hanging
above
off his
Orion's
belt that we colloquially call Orion's penis.
Some childish people may do, Barney. Maybe
It's funny.
But
us more cultured people.
the middle star of the 3 is actually the Orion Nebula. It's not a star. It's a very dense hydrogen nebula that's a stellar nursery, basically.
Cool. The Moon, Mars, Venus, and Mercury seem very close at the moment, all over in one cluster. I'm just looking through my little sky map. I'm trying to find Orion, but I can't find him at the moment.
That's below the horizon.
Where should I be looking? Oh, below the horizon. No, I can look down as well.
In the east.
East. Hang on. Right, let's try and look east. Yeah. Hang on. I'm looking east. Andromeda. Oh, I found Andromeda.
Andromeda should be quite high up.
It is quite high up. You're right, John. Andromeda's pretty high up. Aldebaran.
Aldebaran. Go to the left of Aldebaran. You should find Orion.
If I knew what I was looking at, I could go outside and look, but I wouldn't have a clue. All I see is stars.
Oh, is Orion not going to come up this time of the year in the UK then? Will I get to see him at all then?
Well, Orion is at its highest in the sky and due south at midnight about New Year. So it's the winter. It's the kind of winter, the main winter constellation.
Is it? Okay, I found him, but he looks very different. So the picture that on this wretched thing, the Orion that I'm used to, this guy looks like he's like got a dead leopard in one arm, and he's holding the other arm up.
Are you using Stellarium?
I'm using I don't know, something on my iPhone, and he's got M4, M43 in the middle of him, between Safe, Rigel, and can't really read that one. Something else. Well, there's Betelgeuse. That's Orion, isn't it? Yeah, Betelgeuse.
Yeah, M42. M42 is the Orion Nebula.
Is it? Okay. Right, so that is Orion. It's just not the Orion I'm used to seeing. I'm used to seeing what Barney said. You know, his 2 shoulder blades, his 2 legs, and then his belt, as I like to call it.
I always switch off the zodiac imagery, personally.
Yeah, I've never played with this thing before. I'm just having a look now. It is below the horizon at the moment, but it should come up later on tonight, I think. It's odd. The moon's normally coming up, you know, where Orion is, right? I'm looking east at the moment. Yeah.
Yeah.
But suddenly, according to this, the moon is over in the west at the moment.
Yeah. The moon's almost a new moon. It's close to the sun, so it's between us and the sun.
Right. Okay.
John, do I need to turn the ground off in Stellarium to see this?
Yeah, to see Orion.
Okay. Done.
How's the ground in the road?
Yeah, I couldn't see it. I was trying to find Orion. It's like, where was Orion got?
Yeah, it's below the ground. I should have said it's below the horizon. I had a little trouble looking for it.
But yeah, we'll give you an idea of if you got Orion's belt and you go up to the right to Aldebaran and keep going at the Seven Sisters, the Pleiades M45. To give you an idea, if I put the DSLR on the telescope, I can't fit that in the frame.
You can't fit it in the frame.
No, I would have to take maybe three.
Hang on. So you go up from Orion, you said, towards which Aldebaran? Did you say?
Yeah, if you follow the line of the 3 stars of Orion's belt to the right,
to the right, yeah,
Aldebaran, and then a little bit further, you get to the Seven Sisters.
Seven Sisters,
or M45 Pleiades.
I can't see M45. M31. Have I gone too far up? M76.
That's Andromeda.
Okay, I've gone too high, have I?
This sounds like motorway.
It does. Which way am I going? Am I going the wrong way then, John? Which way am I?
If you go back to Orion's belt.
Yep, got his belt.
and follow the line of Orion's belt, kind of
upwards,
roughly,
not downwards, upwards.
Yeah, up to the right, you get Aldebaran, and then a little bit further, about half the distance from Orion's belt to Aldebaran, you'll find the Pleiades.
M45, the Pleiades. Oh,
yeah,
I got that. Alcyon, something.
Alcyon.
There you go. Yeah.
But yeah, that's to give you an idea of the field of view. If you put a DSLR on the telescope, it wouldn't fit in the field of view. You'd have to make a mosaic.
Really? That tiny thing wouldn't fit in. The M45 wouldn't fit in.
Well, I can try and I should really be on my PC show you this, but I should maybe get a link actually, a new link. Where are we?
Now that's amazing because it's below the horizon where I am at the moment as well. Only just, so I suppose later on it will pop up. It'll be behind trees. That's the trouble where I am. There's a lot of trees around, so I don't get to see stellar objects until they're right up. So I was hoping the moon will be full soon, and I'll be able to use my my P900 on it.
Oh, flat Earth camera of choice.
I don't
exactly.
I don't know if you can see the red box around. That's the field of view of the camera.
Wow.
So you couldn't even get it all in. Wow.
And if you go to M42, actually we were talking about the Horsehead, weren't we?
I was anyway, but that's nothing.
So that's Horsehead. Is that a nebula? Is it?
Yeah.
Yeah. So this is.
What does nebula actually mean? A lot of stars together, or what's a nebula? When
gas and particles, whatever.
Gas.
All right. There's no stars there. It's just clouds of stuff.
Well,
don't care about luminaries, man. They're just lights in the sky.
So that. You see the where are we? You see the red box again? I don't know.
I can barely see it.
Hardly see it. I'm imagining there might be red there.
Well, that's the Horsehead. Where are we?
Oh, yeah.
Aren't the Pillars of Creation in Orion Nebula? Is that what they are?
No, they're in the I think it's the Eagle Nebula.
All right.
Which is quite low. I've never managed to photograph it. It's usually
when you photograph it, John, do you then put all this color image treatment on it, or you see these amazing ones? That one that Simon Mandan's got on his wall, right? Which is, I think, the one that Pip was just talking about, the Pillars of Creation. Yeah, all those amazing colors and stuff. What does it look like when you take a photo of it?
Well, that's the Hubble palette, I believe.
Right, Hubble. Okay.
So it's really it doesn't look like that. It's red.
I mean, what does it actually look like?
Well, they tend to, I can't remember. I'm not a big fan of it because I think it's better just to be faithful to what it actually looks like.
I agree. Yeah.
But they substitute certain colors for like sulfur and oxygen and hydrogen just to make it really contrasty. But basically, I mean, if you were to describe the universe in one word, it would be hydrogen, because that's the main constituent of the universe, and it's red. So most things are quite red. Oxygen's blue.
So where would I find a natural picture of sort of something like what you see through your telescope, so I could actually see, what you're taking photos of roughly, what an amateur could. Because I'm looking at these Orion Nebula, right, and they're all, like you say, they're all probably treated by NASA with a palette, and they all look pretty amazing, psychedelic things, yeah.
Well, the images on Stellarium, they're pretty accurate. They're pretty good.
My first photo of the Orion Nebula. That sounds good. That sounds like someone has actually done it on Reddit. Yeah, looks like a sort of green splodge. Still, it's pretty impressive. I mean, it's.
How would I get a link for the to present on the laptop? Can't remember how to do it.
You would need to open a Chrome window and then go to Terry's YouTube page, and then Terry can drop you a link in the in the YouTube chat, and then you'll be able to open it in Chrome.
What's your surname, Terry? What's the channel called?
Terry Davies. Delta Alpha Victor India
Echo Sierra.
Echo Sierra, yeah, that's it. For some reason, I kept trying to say X-ray instead of Echo.
Terry has a new subscriber.
I'll chuck the meeting link there because you're already in the meeting.
You can get another link, can you? Because I thought you couldn't join.
No, you can rejoin. You just can't join.
But you can rejoin from a different PC.
You can rejoin from a different PC, yeah. As long as you got the link.
Oh, really? So I could share all my amazing photos of that I've just got from this guy from the thingamajig. Oh, I should try and join them. Shawn might be interested in seeing that. I know Rumpus has dropped off, but how do I join? No, go to YouTube first of all.
Well, actually, if you just go to, I think
I've got it. That's it.
Yeah, I stuck the meet link in the, and then of course you can then share your. I don't know if you're using Stellarium or something else, but you can then share that window to meets, and we'll all see it.
So how do I join again? How did you say I join, Alan? Like I'm on my Mac now. I go to the.
Right. If you go to Terry's YouTube channel, so you pick up the live stream.
Yeah. Oh, ready to join. Yeah. All right. Yeah.
In the chat, I just chucked the join link in the chat. And you just click it.
Just let me in. Amazing.
Yeah.
Right, I'm going to drop on this one and join that one.
This is so hands-free. Just doing it this way, Alan.
I think I'm here.
Well, once people are in, they can get in and out. But it's
Can you hear me?
Yeah,
we can hear you.
Oh, there we go. Fantastic.
Right. In fact, it felt like you didn't even leave.
Yeah,
exactly.
I don't think you did. You're just fibbing this.
Thanks for the vote of confidence there. So if I click present, while John's doing his, am I doxing myself? Hopefully not. Okay. Sorry, John, if you want to share, I will stop sharing. But here we go. Here's my...
more evidence for the globe.
Yeah, here we go. So I'll flip through it quickly because you won't want to see all this. That was a conversation.
I'm not going to read it all.
Are you seeing anything?
Yeah, we're seeing pictures.
Right. Yeah. I'll show you the pictures. Don't worry. So there's the picture of one of them. There's a retroreflector. Yeah, there's the lunar pronouncement orbiter. Yeah, I'll be reading through this in the video. Yep.
Oh, your bank routing.
There's a few of those. There's a few of those reflectors on the moon, actually.
There, I'll show you. You'll see really a lot of detail. So there is the signal to noise, right? So that's where it's actually bouncing. It's only about a meter where it bounces. This is all the stuff they've picked up. There's 5 reflectors left by Apollo 15, 14, 11, and also the 2 Russian ones, Lanakud and
you got the map for that too? Because I know there's a map for that.
Yeah, there you go.
Yeah, there's the map.
Are you seeing it? Yeah, which shows you exactly where they're pointing at. See, he's given me some. So these are all from this guy who's at this Apache Point Observatory, right? So this is his stuff, 20 hertz pulses. And you know, Alan was talking about gates. He talks about this gate as well. Yeah, you'll see it in a sec. He talks about this gate thing that Alan was talking about with radar, which is quite interesting. So 50 pulses in the air, 2.5 second round trip travel time. So basically, you point a strong laser at the moon, you aim for where the reflectors are. Thanks, Buzz Aldrin. Yeah, 3.5 meter dish. Here's 2 of them again. This is the one AS11, and this one I think is AS14. By the way, I'm going quickly because you won't want to see all the guff. This proves there's a number of observatories doing this, right? So this is the Goddard one. Here's the one at Wetzel. Here's the McDonald one, the one that I think he's working at. And then this one is the Barda 5.3 meter SLR dome. This is the site that he's at. He's showing us, what they got in the observatory. Gives the coordinates, what the elevation is and everything, which is quite interesting. Here actually is a close-up. Here is the reflector, I assume. Here it is actually firing its laser. Here's the laser, warming up, I suppose. Pretty big and very green. It looks very exciting to me. Here's the detector that they're using, trying to get rid of jitter, apparently, which causes them all sorts of problems, the guy said. Here is it actually signal firing. Yeah, I think they've got a lot of cryogenic cooling used here. Here's the thermal control, computers, APD detectors that I'll be going through. That's the results you saw, and then I go into what that actually proves to debunk QE. There's the landings. There's some more tests. This was the list. I don't know if you're seeing this, John. Is John still there? Oh.
Hello.
John
dropped out. Yeah.
Did he drop off? It's a shame. So this was the list that him and Rumpus were interested in of all the things that are moving it away, and then these are the movements. Do you remember I said there was 4 meters lunar crustal tides, Earth crustal tides 20 centimeters, and the solar radiation pressure of 4 mil. And then I think that's it. So yeah, some interesting stuff that will come up, which I will of course go through in a bit more detail, when I'm actually doing the video.
Right.
And you have the whistle stop too.
Can I get explained the laser going to the moon and back, how they calculate the distance with that?
1,000, 2 1,000.
Yeah, so they obviously look at the timing signal. I think they gave the equation there of how they actually calculate it.
I was blocked up a bit, and I wouldn't be able to understand an equation.
I can tell you what it is, Terry. 10 times 10 to the minus 6 seconds, which is 10 microseconds, or 10 1/millionths of a second. In that time, light will travel approximately 3,000 meters. It's 2,997 if you want to be really, really exact. But of course, because we have to send the signal out, wait for it to get reflected and for it to come back, we have to wait twice as long. So what we say is that in 10 microseconds, we know that if we get a return after 10 microseconds, the object is 1,498.98 meters away. Okay, so after 10 1/millionths of a second, if you get a return, the object is basically 1.5 kilometers away. So if it takes 3,000 microseconds, it's gone 450 kilometers and back.
So they're looking at, just to help you, Alan, 45 nanoseconds for the gate. So you know your time into the gate. Yep. They're looking to bounce it off the retroreflector at 45 nanoseconds.
I think that's the gate for their output pulse, not their not their.
Yeah. So it says time into. Yeah, it says time into gate. If that is any help at all.
Yeah, I'm probably need to look at the whole specification, but a 10 nanosecond gate sounds to me like the length of time they let the laser light out for.
No, so hang on. Yeah, hang on. I'll tell you that bit because I've got that too, and then I've got the return there. So 20 hertz pulses, 2.5 second round trip, yep, to the moon. Yeah. And they do 50 pulses simultaneously.
So they'll fire for 2.5 seconds.
Yeah, that's what it says. Yeah. I'm just looking at 20 hertz. 2.5 second round trip.
20 hertz. They're doing if there are 50 pulses in the air, they have been transmitting for 2.5 seconds.
There you go. Yep.
Yep.
They're transmitting for the whole of the round trip then. So they're going
and I'm
bing, 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 and then it starts to come back.
And I'm guessing that because see, there's when you're what we talk about is the PRF, i.e., how fast you're firing the pulses, and in this case, it's 20 hertz. On the radar that I worked on, it was 250 hertz.
Mm-hmm.
But then you also have another thing that's important is you have the pulse width of the transmitted pulse.
Mm-hmm.
Okay, and in our case, our pulse width was 10 microseconds. So the transmitter is switched on for 10 microseconds. And transmits a pulse of radio frequency or electromagnetic waves at whatever frequency you're using. In my case, it was 0.1 meter. In this case, it's somewhere right in the middle of the visible spectrum in the green. So I'm guessing about 700-800 nanometers. And I'm guessing that
I can't see the spec for that, which is interesting because you're right. It's green light, isn't it? They've shown it in all the pictures.
It's green light. I mean, you can say, well, green light is nominally, and I forget what. I know infrared is sort of 650. Infrared, beginning and bottom end of the red spectrum is sort of 650. I think green is sort of 700-800 nanometer. Sorry, it's getting shorter, is it? Because it's getting shorter. So it'll be so if red is 650, it'll be in the 500. It'll be in the 500s, maybe probably in the 400-500s. I'd have to look. And right this minute, I'm not going to grab Google and go and look. I could, but and then that's the other important. But the time that you said, which was a period of nanoseconds.
Yeah, 45 nanoseconds.
45
nanoseconds. What they called the gate into the gate. They said.
Yeah, so that would be how long they switched the laser on for. So you gate the laser output, and
right, because the graph they're showing is the signal coming back from the thing it's bouncing off.
Yeah,
because it's like a picture of a lot of dots, but there's a lot of dots at that 45 nanosecond point. Yeah. Hang on, I'm just trying to look up the spec if I can find it. So while you keep talking, I'm still trying to see if I can actually find it. It's interesting, isn't it, to know?
Well, yeah, because 45 nanos, without knowing what the axes of the graph are, it's...
the axes of the graph are time. The axes are time in minutes. Yep. So either they did a number of observations over like a 12-minute period. Yep. Yeah. And then the other axis of the graph is what they're calling time into gate in nanoseconds. The longest at the top is 120 nanoseconds, and they're getting nothing at that point. But they're getting a really big strong line cluster at 45 nanoseconds. Yeah. There's like a dark line, over a 20-minute period. They're getting a lot of hits at that point.
Yeah.
But what does that mean? Does that mean they're opening the gate for 120 nanoseconds?
Without, I mean, they may well be just opening the receiver at the. See, what they could be doing is to stop the receiver being constantly saturated.
Yeah, they said there's a problem because apparently when it hits one of the little thermocouple things, whatever it's called, what are the little thing, photon, multipliers? Yep. Apparently, there's got a problem where it has to reset, and if another thing hits it, it doesn't actually trigger it. Do you see what I mean? Because it takes some time for those multipliers to reset themselves, basically. Yeah.
Yes, of course, because we're see, I'm so used to thinking wavelengths like tenths of a meter, which is effectively radio, where we are using a radio receiver, and we are still coupling the electric and magnetic fields to receive. We are not counting photons yet.
Yeah, exactly. Whereas they're counting photons, aren't they?
Whereas they're counting photons. So I'm guessing, although obviously not optimum, because obviously optimum is to have your range gate open for the entire period that you're expecting to receive signals for. Yeah, you just open your range. You make you effectively, because it's a camera exposure, you make your camera exposure at the time you expect the signal to come back to you.
Yeah, and if you see they're maxing out at that 120 nanoseconds, the graph is pretty empty. Yeah.
Yeah. So they're literally, it'll probably tell you, how long after they started transmitting that that they open the gate to the receiver. Obviously, with the radar, we fire the transmitter and open the gate immediately, and then we shut the gate after whatever we want our maximum range to be. In the example I have, we would keep the gate open for 3,000 microseconds or 3 milliseconds, and then we would have a 1 millisecond intertrace period, and then we'd repeat.
Right, the graph shows the photon pulse return times. Now, how can it be returning in 45 nanoseconds? That doesn't make sense to my brain.
I'm guessing what they're doing is they're actually showing you,
because it's going to take 2.5 minutes, isn't it? Seconds, sorry.
So basically, you've got a graph with a fucking long axis.
That's right. 12 minutes.
Especially 2.5 seconds. Especially when you're dealing in.
Hang on. Let me just reshare the graph. Hang on. Let me just reshare the graph so we can have a look at it. Sorry, just bear.
That would be a damn good idea.
It would. I know, because we're all talking about it, so it'd be much better. Can you see it yet?
Yeah.
Let's see if I can make it bigger. There we go. Right. So you've got what they say time into gate nanoseconds, 0 to 120 nanoseconds. And then you've got just time in minutes, which means they're taking a lot of samples, right? For 12 minutes. Yep.
Yeah.
This apparently is all the pulses coming back at this, like I said, 40, well, maybe nearly 50 nanoseconds. Yeah. So what are they actually doing? They're pulsing something out. But what
I'm guessing, it's time into gate, because that's fine. You're going to have you've received gate open for 120 nanoseconds. I.e., but what that's not, and they are.
So does it mean this one took longer to come back, Alan? Does it mean that I'm firing something? Yeah, and does it mean that this one up here was a slow one, whereas all these lads came back in at a very regular? Because they're saying this. So what they're saying, right, when you read the gubbins below this, is it says this. They said the whole thing represents 30 meters of bounce, right, like a 30-meter reflection.
Yes, that would be right.
Represents 1 meter. They said this line here, this 45 nanoseconds, is 1 meter. This very thin line.
Yes.
Which means it's definitely bouncing off the reflector, but I don't understand how 45 nanoseconds means 1 meter.
Because what they do, because they know what they know when to open the gate to get the expected. What they're doing is they're open this, and this would be where the flurfers would attack it. They are opening because they're looking for, like you said, 4 meters or whatever it is.
1 meter square of the laser refractor.
Yeah, and so basically you're looking for a difference in from the bottom to the top. Would represent a difference in distance of, like you said, about 4 meters or whatever.
Oh, right. I see what you mean. So you've got a curve there. These are very, very small nanosecond things. You fire your pulses out.
So basically,
I see. And so this
basically,
means,
why do we want to look at the 2.5 seconds when we're trying to measure a 4 meter difference? We're going to open it at the right time. We're going to open it and close because we have to measure it really freaking quickly because we're measuring light moving 4 meters.
Yeah.
Right. We're measuring it down to light moving 1 meter.
Yep.
Right. Light's going to move 1 meter. So effectively, light is going to move 1.5 meters in 10 nanoseconds.
Light is going to move 1.5 meters.
In 10
so they're saying this is a 30-minute period, right? So I fired my light, right? So my light's
you're firing your lights out consistently for that length of time.
But I'm opening my gate over a very small bit of that reflection window, right? There's a lot that I'm not
imagine this is the bottom one is the length of time we run the whole thing for.
This way,
but the vertical axis is your 2.5 second return time. But you're only plotting
a little window of that.
You're plotting the little window, which is why we have the little tiny window of that.
Yeah.
Because we know that grossly it's that far away. So
yes, that's right.
We don't we don't want to have a plot because we want a plot that's accurate down to the nanosecond, i.e. 10 to the -9 of a second. Right, that would mean we would have to have a graph that is
stupidly big.
2 times 2. Well, you'd have to have 2 times 10. You'd be like out to 2.6.
So basically, what's happening?
You'd have 2.6 times 10 to the 9.
Yeah. So what's happening is this. I'll try and explain it. Right. We've got our mirror on the moon, and then we've got the soil around it. Okay. We're opening the gate in the sweet spot when we are getting reflections pretty much from that area and that area around it because of the time that it's coming back. The fact that we've got so many hits. But the fact we've got so many hits here means these are definitely reflecting off something. Yeah, sure, these ones are reflecting off something, but not very reliably, right?
Correct.
Maybe these ones hit the edge, right? And maybe these ones
or they just hit
a bit of a rock or something or whatever, something else that was near to it.
Yeah, because that's basically vertically gives you a fine look at the distance.
I see the rover.
From the Earth to whatever it bounced off.
Yes.
And so some of it's so of course. If the closest bit near it is actually no, because of course that by the time that beam gets to the moon, it's covering quite a wide area.
7 kilometers. 7 kilometers.
So you're going to get stuff that is closer.
Random crap coming back all over the place.
You're going to get the random. You're going to get returns off stuff that is closer to you, and you're going to get returns off stuff further away.
Don't you think this is interesting, Alan? Look at the 2 minutes? That's 1 minute. Look at about 1 minute. It looks like they turned it off because look, there's a big white line there, and look, there's another white line here. Can you see these vertical white lines?
Yes.
So they really don't get many signals see here at this 8 and 9.
And there's one at 4 as well, isn't there?
There's one about 4 here too. Yeah, exactly. And there could even be one about here as you see what I mean. There's spots where they're getting a lot less back, which is probably where the pulse stopped for a second and they
Well, could
be anything. Could be a cloud in the way.
I mean, atmosphere. Let's face it. I have a degree in electronic engineering with 3rd class honours. I'm making an educated guess because I also have a background in radar, which is doing this sort. Which is what this is doing. The more I look at it and the more I think about it,
the clearer it gets. Yeah. What surprises me is this 1 meter, right? Is this, they say, because I read the blurb, this meter is this bit. It surprises me that the mirrors must be very, very accurate. Do you see what I mean? Because look, they're looking at nanometers here, right? For the bounce. You'd think a mirror might not be perfectly flat, for example, and that would change.
Well, it's not a mirror, it's a retroreflector.
Oh, is that not a mirror?
No, it's a prism. Because, and you know why they use prism? Because retroreflectors are very clever. They can gather. From what I remember of looking at the picture of a retroreflector, each retroreflector in the array is about 4 inches. I think it's hard to.
What are they though?
No, a bit less than that. 2 inches. So each of those retroreflectors.
What are they? These retroreflectors?
They're prisms. They're circular prisms. What happens is the light. Right. The channel stand up. No, there's a channel on YouTube where they're actually talking about. They've been putting the purple line in London. Mm-hmm. Well, if you go on certain tube stations, there's a load of retroreflectors, and they've actually got a laser measurement system that spins the laser around and fires the laser at all these retroreflectors continuously, so that they can measure movements to like 1/100th of a millimeter. But they do it by using prisms, because you're guaranteed to get the light back directly at you.
That reflector is basically looking at the outside of a pyramid.
Think about a bicycle reflector.
The really important thing that they do is that they send the reflection directly back from where it came from.
Yes.
But if you look at the timing, did you see the timing, John, that we were looking at earlier? Have you just returned, or have you been here for a while, John?
I've been looking just the last couple of minutes. Yeah, I can see it.
So I don't know if you saw my main the main bit that I did. Where was it on the thing when I had the keynote stuff up? So I was looking at this because I had that list that you and Rumpus wanted to have a look at. Where was it? Yeah. This was the thing about all the problems that they have. So the Earth's polar axis. Do you see what I mean? List them. The stations due to the tides, the Earth's crust, the weather, and the pressure of sunlight. And this was what the guy said on his slide on the main problems. These lunar crustal tides of 4 meters, Earth crustal tide 20 centimeters, and solar radiation pressure of 4 millimeters.
Jeez.
Yeah. So, but then I got up this full list here. But yeah, I didn't understand this one either, Alan. So if you look at this one,
right,
this is a calibration profile of some sort. Yeah. This is time in minutes again, from actually reading this way, isn't it? Up to 50 minutes.
Yeah. So that's how.
Transit time residual in milliseconds, not nano, milli.
No, that's nanoseconds, because that's NSEC, not MSEC.
Oh, NSEC, you're right. Okay. So that's 5 nanoseconds they're looking at there. And look, they're getting a lot of hits in that, which I suppose is the black line on the other one then. That must be the 5 nanosecond width there, yeah?
Yeah.
These are the 1971 results, by the way.
Yeah. And again, because you are basically literally counting photons.
Yeah, these are individual photons, aren't they? 1, 2, 3, 4, 5.
Essentially, yes, it will be that level of return signal that you are pretty much counting.
They
photons.
said it's amazing. Look, they said they're sending out. Hang on, let me find it. It'll blow your mind. Like, hang on, I actually had the number that they're sending out, and then how many they're getting back. Hang on, let me just find it. I think it's here. It's like 10 to the -7. Let's just find it quickly. Laser pulses. There's not that one. I'm sure they're sending out 10 to the -7. There we are. Out 10 to the 17 photons aimed at the reflector.
And they get
only
back
one is received back. Right. I mean, that's just incredible, isn't it?
Yeah. I actually saw the 10 to the 17 quoted, and the size and how big the beam was at the moon, and how much,
6.5 kilometers. Yeah.
And I did actually calculate it out, and I came back with so they send out 10 to the 17 photons, and they get back one or at least single digits,
even under good conditions. So they can be identified as the originating from the laser, because I guess it's very monochromatic, like this green light. Yeah. I guess that tells them that it isn't just some other random bit of light that's flowing into their. Did you see the observatory pictures, John?
Did you read the bit underneath it for the measurement between New York and Los Angeles within a?
Yeah.
Oh yeah, where was that?
Just underneath that bit you were reading, the last sentence.
Yeah,
this is one of the most precise distances made, equivalent to the action to determine the distance between Los Angeles and New York. Wow, to within 25 millimeters.
Yeah, I was talking about
0.25 millimeters, quarter of a
meter.
millimeter.
Last night.
A hundredth of an inch.
Yeah, that's the accuracy of our understanding of the nature of light. That's not just unique to that experiment. That's when who was I talking to? I can't remember. But when Richard Feynman finally unraveled quantum electrodynamics and the modern theory of electromagnetism, that's the margin of error that you're talking about if you're measuring the width of the United States. Yeah.
Now I think they've mocked this, because I think you might see it going up if you had a bit of cloud, but you're not going to see it bouncing back. This must be a mock-up, right? Bouncing off a plane, maybe, or something. Do you see what I mean? Or maybe it's 3 shooting up.
Yeah, 3 separate locations. Sure.
Time lapsed.
Yeah, it could be. Yeah, it could be time lapsed. But I mean, it looks like it's bouncing to give you the idea, which is why I picked that picture. So here, John, this is the one I think the guy's at. Here we are. This one here. He gives the coordinates and everything. It's got a 3.5 meter dish that he's working on. I'll go for it quickly. This is the, and that's actually what he is. There it is firing. I guess that's time lapse as well, because look, one. So you've got several laser sites, doesn't it? It looks like that.
I think what you're seeing there is just the fact that there's a lot of light there's a lot of light escaping out the sides that is lighting up the building, and right there you can see.
That looks like a lot of glow, isn't there? Yeah, there's a lot of glow.
There's a lot of glow escaping.
Must be a big laser ring. I mean, look at that laser ring. It looks huge, doesn't it?
More like a laser cannon, isn't it?
Laser cannon, exactly. And then
sharp with that.
They use these special APD, whatever that means, detectors. What's that? A single? What's that symbol mean? Photon?
Gamma.
Gamma. Is it?
Gamma?
Yeah, that's a gamma. I'm guessing that's what they use for essentially saying will detect single photons.
50% efficient.
Oh yeah, that's a symbol for photon. Yeah.
Is it photon? It is photon. I thought it might be a photon detector. Okay.
Gamma's upside down from that.
All right, so photon, which is brilliant. And here he's given us a look at the inside of whatever it is. I suppose the laser actually firing. So the telescope's up that way. He's saying, timing electronics, the lasers in here. That box we've just seen. The detectors are in here. It's all very compact, isn't it? And this is all thermally controlled, I suppose. They need to keep it cool, I guess. Then the results, of course.
When you're using a retroreflector, you really want your receiver right where your transmitter is.
You want it really close because you don't want to.
Because as we
down
said,
anything, yeah.
When you hit the retroreflector, it sends all of the photons back directly in the direction they came from.
Oh, does it? So that's why they want that telescope all built into the same thing, yeah?
Yeah, that's also why they use retroreflectors, because it's not a mirror, it is an array of retroreflectors, because they will throw back the photons in an optimal manner.
So what does this mean, John? Sloan, 3.5 meter, and solar. What do these things mean?
Guessing they're the names of different telescopes.
Yeah, basically.
All right, and it's a 3.5 meter that they're using.
Reasons, aren't you?
Sorry?
Those 3 beams are coming from 3 different sources.
I assumed they're only using 1 beam, but maybe
I don't know why they would use 3. It seems pointless.
If that's a razor Lee, is that the same picture as wherever we just saw it? Is that the same thing as that? Is it? Is that black thing there? That looks like it.
Tony.
It? Yeah.
One thing. Some of these observatories fire green lasers up the optical path of the telescope where it's looking, in order that they can because it actually allows them to calculate stuff about the
jitter.
Yeah, I mean, these aren't pictures I picked up. These are the ones he gave me.
No, but I'm just saying.
But these are the ones he sent me from his pack. You see what I mean? That he said, yeah, this is our experiment, and da da da. He went on, about it, as it were. I've cut some bits out actually, because otherwise I'll bore everyone to death going for all this. You can imagine.
It could just be that those other 2 telescopes that have been. Oh, can we point all the lasers up in the same bit of sky so that we can get a nice photograph? To take a photo for because obviously it's because it's a cloud. It's also noticed that there's quite a lot of cloud,
isn't it? Yeah. It's not going to go for cloud.
So like it's probably we can't do. Can we point them? Can we point them all up there so we can take a nice publicity photograph?
I agree. I think the interesting thing for me is that people go NASA conspiracy. It's all NASA. Look, this one might be associated with NASA. This one's independent. Yeah, this one's independent. Yeah. You know what I mean? This Bavarian one, Goddard, I think, might be associated with NASA, but at least there's 2.
I was just looking at the angle of those lasers. They wouldn't be all pointing at the same spot.
True.
Well, they're all pointing at the same spot on the cloud, because you can see the 3 laser lines essentially meet at the cloud level. Yeah, in that picture.
I think this is, for me, this has got shenanigans written over it. I reckon it's just, as you say, a publicity shot to show the idea of a bouncing something off the moon.
Yeah.
I suppose. I don't know.
Yeah. It looks like they've gone, stick that one there, stick that one there, stick that one there.
Yeah.
If I put the camera here, we can point them 3 lasers there.
Get a nice publicity shot.
They'll all appear to be on the bottom of the cloud.
Now,
and get it all in one
the flatties can attack it, but I have put, really specifically all of my references here. If they want to pick on it, you know what I mean? I was very careful of what I chose for that reason. Do you see what I mean? I didn't want to, there's another one, I think, sideways going out, and they've again enhanced that a bit with the sun, haven't they? I suppose. But that's probably photoshopped in, actually, isn't it? I don't think that's even a laser, is it?
I think that's just a bit of lens flare.
Yeah, I think it's a bit of lens flare that was conveniently looked like it could be a laser. Yeah.
I think that's just a nice bit of lens flare.
And again, that looks like CGI to me.
Yeah, I think that one could be.
Yeah.
Actually, do you know something?
Yeah.
Given what I know of photography and camera exposures, that's the least staged image that I've seen.
This one, really?
Yeah, well,
it's a long exposure.
It's an obvious long exposure.
Bang, bang, bang,
The moon is, as usual, really effing bright.
you're right. I see what you mean.
And the stuff you're getting back off the laser is actually really bright because it's a. And I like the way it looks like the and I like the way
the Death Star.
The Death Star.
Yeah, but I see what you mean. That probably isn't.
That's
It's probably
no
the
moon.
long exposure, isn't it?
That's no moon. That's the Death Star.
The horizon is hugely illuminated, that's a long time. That looks like all my time lapse I've done.
Now that looks like CGI to me.
Yeah, nah, that's real.
I don't think that's real somehow.
That's a.
I think I've spelt lock nude incorrectly.
That could actually be a photograph of the LRO satellite.
Really? I don't think so. That looks like it's rendered to me.
Yeah.
There's nothing in orbit that could take a picture of the LRI in that
exactly
position.
What's there that could take the photo as well. Yeah. I think they actually said this is an artist's impression where I got it from as well, I think.
Yeah.
And look, early on, the Soviets used just a ruby laser, which is interesting. Though they obviously now are using whatever the green ones are, which aren't rubies because they're not red, are they? But yeah, when they first did it. So QE was right when he said that the 62 team did. But the point is that 62 team did not get that kind of result.
You also, you can get a result when you just bounce it off the surface, as you can see from the scattering all around.
Yeah, here, exactly. This scattering shows you can
can't get an accurate measurement down to the inch or centimeter.
Yeah,
which is what they're trying to do with these, is determine the position of the moon and its regression, or whatever you call it, getting away from us further.
Well, this was the interesting thing. General relativity, almost all of the most accurate tests of general relativity are currently derived from the LLR to the Apollo arrays. Yep. Over the long term, we expect to improve the current accuracy by 100. These things, G dot violation. This will address many tests concerning the validity of general relativity at a new level of accuracy. Yeah, and this one, LLR, has become one of the strongest tools for testing Einstein's theory of general relativity in the solar system. No violations of general relativity have been found so far. However, the basis for all scientific analysis is more high-quality data. Just so it's really interesting that this measuring the distance is more than just,
and the basis for it is more high-quality data from a well-distributed global LLR network.
Yes, so multiple, things doing this, not just NASA testing it once.
Yeah, and I'm sure some of it will actually involve simultaneous measurements from more than one location.
Yeah. Well, when you see the amount of effort, as I say, that they put into this stuff, all these things that can change the distance that I spoke about earlier. This was the one that got me. The pressure of sunlight. I don't imagine sunlight even having pressure. Pushes the moon orbit off center. This is a small effect, about 3.6 millimeters. Still, that's quite big, I think. But it's particularly important since it mimics the effect of EP violation, whatever that might be. What is EP? Equivalence principle? No. Equivalence principle. EP is equivalence principle. So basically, they're saying the sunlight is pushing the moon. How can sunlight push the moon?
Well, photons are hitting it, aren't they, and transferring their
you
energy.
mean it's actually got the energy. So the sunlight is so bright, it's pushing the moon.
Well, there's an awful lot of bloody photons coming from the sun, aren't there?
No,
remember, we can go outside and we can during the day with a DSLR, we can't count photons. There's too many of them. That's why DSLR and even your phone camera generally aren't too noisy in daytime, because the noise is, because what you have to remember is that when it comes down to exposure, there are only two variables: aperture and exposure time. The sensitivity side of it isn't really exposure at all, because remember, exposure allows you to collect a certain number of photons in your bucket. Now, when you've got millions, when you've got 10 to the 9 photons in your bucket, a variation of 100 photons is going to give you basically no noise at all. When you are looking at 10 photons, a variation of 100 photons arriving gives you a rather not good signal to noise ratio.
But what amazes me is like solar boat,
which is why they're using very specific monochromatic light,
so they don't get muddled up by all the other bits of random light from stars.
And there's something else I will bet you. I will bet you that it's in one of the gaps in the spectrum of the sun.
You're probably right as well. Yeah.
Because
well, of course, yeah. Otherwise, you get it bouncing off the moon, won't you? Yeah, from the sun.
Well, but also remember, retroreflector. The light coming from the sun will be reflected back at the sun. It won't be reflected back at you, unless. Well, even at full moon, where the sun is, it's going to reflect it at the sun, not at Earth.
So this
I think a cheap example of a retroreflector.
Does this not amaze? Sorry.
A cheap example of a retroreflector is a bicycle reflector.
Yeah, when they've got those prisms on it. Yeah, they're very directional, aren't they?
Yes, indeed.
Does this not amaze anyone else though? That the sunlight is pushing the moon 4 millimeters away. It's like a solar boat, right? If you've got a big enough solar sail, you could fly a rocket just using the power of the sun.
Planetary bodies.
Yeah.
If you made a solar sail the size of the moon, you would have a force to reckon with.
Exactly. Why doesn't that happen then? Why isn't the moon constantly pushed more and more?
Gravity. Gravity.
You never heard of gravity?
Nah, it doesn't exist. Made up.
There's on the same principle. One of the hypotheses for diverting an asteroid that's on collision course with Earth is painting one side of it white.
Oh, I heard of that. Yes, and it will try and melt it, or
no, it would get pushed by the solar radiation.
If we could get to it fast enough and spray it with something that's white.
Yeah. I wouldn't like that paint job personally.
Yeah, and I wouldn't like to have the whole of the Earth depending on managing to paint it.
But yeah, the solar wind would be sufficient to alter the course of an asteroid.
What I don't understand, Alan, is with a 4 millimeter variation due to whether the sunlight is on or off, we're still trying to measure on this seconds. Seconds, I suppose. No, it's seconds. It's not distance, but still. What I mean is, there's a lot of this stuff. Here we are. There's a lot of stuff messing around with how far you are away from it. You see what I mean? This is varying you by look. This is 4 millimeters up and down. This weather apparently, it doesn't say how much, but look, a few millimeters up and down from weather loading or whatever they're calling it. The Earth's crust due to whatever post-glacial rebound, which sounds like glaciers have moved off and the Earth is springing back up. This is 35 centimeters. This is 10 centimeters. And these are big effects when you're shooting one of these things. And look, this polar axis sounds like it's a nightmare as well. Because look, it says they've even their own agency to keep track of them, the International Earth Rotation and Reference System. And Riley says the Earth doesn't rotate. There's no proof of it. And yet there is this body that...
they're all in on it. Or fools.
IERRSS. He's probably never heard of them.
But you know what I mean? Look, it's a specific body just to keep track. Yeah.
But if they take lots and lots of measurements over long duration, you would see all these trends in the measurements, and they can be accounted for. Yeah,
they say it's been 40 years, I think, of measuring. They said this guy said 36, but that was at least 15 years ago. Whereas this guy said, "Thanks, Buzz Aldrin." Yeah, but this was in. He did this in 2005, so that was 14 years ago. So look, 30, 40, 50 years. It's been 50 years. Yeah, of course, because we've had the celebration. So yeah, Retro Refractor's been there 50 years. So, I don't know how much they bounce the stuff up for Luna, these two Lucknood ones. And I wonder why the Russians were clever enough to put a retroreflector on it. The reason I've got this, the LRI in, is because they found one of the Russian ones, it says. Where does it say it? Down here, maybe.
2012.
Yeah, where did you see that? Or did you just know that? Oh, here we are. Lunar Reconnaissance Orbiter, which found Lucknood 2 and its position of reflectors in 2010, it says.
Toady?
Yes.
I've just done the math on it. And if you go down to 0.1 nanoseconds, yeah. So if you're looking at 0.1 nanoseconds, you have a range resolution of 0.000149896 meters.
Put that in centimeters for me if you could, Alan. So if you go down to 0.1...
It's 0.14986 millimeters.
Now you confuse me.
It's 0.1. It's 0.1. If you go down to a tenth of a nanosecond,
which we're not. We're only going down to nanoseconds here, aren't we? Or 5 nanoseconds, we said earlier.
So if you're going down to
here we are. Look, 5 nanoseconds. We're going down to this side. Yeah.
Okay, so if your resolution is 5 nanoseconds, if your resolution is 10 nanoseconds, you're looking at 10 millimeters.
Really?
Sorry, 15. If you're looking at 10 nanoseconds, you're looking at 15 millimeters accuracy. If you're looking at 1 nanosecond, you're looking at 1.5 millimeter accuracy, and if you're looking at a tenth of a nanosecond, you are looking at 0.15 millimeters accuracy.
Here we are. 1 millimeter ranging improves constraints by 10 times.
Yeah.
Because they said that basically they've been trying to get it even for these relativistic things. They've been trying to really get it even closer. The measurements. I'm trying to find it.
I mean, yeah. I am now doing the rounding to to the 1.5. But basically, if you have a, if you're able to measure to 1 nanosecond, you are looking at
here we are. Look, so all right. So the dark line shows that a large number come back at a specific time, and hence we're reflected by something quite small, well under a meter in size. But this is under a meter. Photons reflected from the surface come back over a much broader range of times. The whole vertical range of the plot corresponds to only 30 meters or so in range. So it's saying that is about 30 meters.
Yeah, that'd be about right, because you're looking at. See, I'm doing it in the tenths, because I know that the tenths. I know that at 10 microseconds we are looking at 1,500 meters, or 1,498.98 something meters for a 10 microsecond pulse for the round trip time. So that's why having the accuracy, that's why having the timing down. If you've got the timing down to 5 nanoseconds, that's essentially an accuracy of slightly less than 1 millimeter, because it'll be 0.75 millimeters.
So it's amazing. So they're sending 20 hertz pulses of this laser monochromatically, green light. It's going to the moon. By the time it gets to the moon, it's 7 kilometers wide. Yeah. And you're telling me some of that, not much, like 10 to the 17 they're sending out. I don't know, the odd 1 or 2 is hitting that retroreflector at 1 meter. It's bouncing back. It's still on course. It's coming through our atmosphere. And then it's coming back into this 3.5 meter dish that they've got here as well.
And of each pulse, remembering that each pulse is firing 10 to the 17 photons, each pulse coming back, you get 1 photon.
That's just mind-blowing that poor little photon that went out with its 10 to 17 brothers managed to bounce off at 7 kilometers. The lucky one hit the retroreflector. Exactly, and came back in a straight line rather than going slightly off here or bumping into a cloud or a bird or a tree. Comes back and then goes into this 3.5 meter dish, like the one that John's isn't quite 3.5 meters, but like his telescope. Goes in it, hits a camera or a little detector that we've got, which measures photons. Bang, and you get a hit. That's mind blowing. How the flat earthers can say this stuff is fake, I just don't know.
Probably because it is so mind-blowing. I mean, like I said, I've got a fairly, I just about scraped through my degree, and that's fine. I don't claim any more, but at least I have done enough engineering, have enough background engineering knowledge to understand that this is possible to do. And I probably wouldn't have had the foresight to think of it, but at least I have the understanding to be able to understand what it's doing and comprehend what it's doing. And I am so thankful for that.
It's just amazing, isn't it? Just incredible. You see what I mean? Each stage has had to be built up, hasn't it, to work out how to do it. The amazing thing was that they were doing it back in 1962, and they discovered the Apollo 14 one, I think, really quickly. Look, the Apollo 14 astronauts deployed a retroreflector on February the 5th, 1971. The McDonald Observatory detected it the same day. So actually, they were firing a laser at the poor old astronauts on the moon when they were jumping around.
I don't think that would matter. But you know what's really rather useful about that, don't you?
Well, it proves it's real.
Not only that, but it also meant that if there was a problem with the placement of the retroreflector array, they had on-site tech to fix it.
No, exactly. So that's because apparently, look here, the NASA attempted to detect Apollo 11's retroreflector while Armstrong and Aldrin was still on the moon. See, but they didn't succeed till later. You see them, they were aiming in the wrong place. Yeah. So when Armstrong and that were up there, it didn't work. But when the Apollo 14 went up there, as you say, they got it the same day. And then the Apollo 15 retroreflector was deployed July the 31st and was detected McDonald. So this McDonald Observatory must have a very big laser, right? Because they seem to be the big boys who are bouncing the most off. It's incredible, that. I like this quote as well. Look, quoting from James Hansen's biography. For those few misguided souls who still cling to the belief the moon landing never happened, examination of the results of 5 decades of LLR experiments should evidence how delusional their rejection of the moon landing is. I love that quote.
Yeah.
Well, I mean, you can't argue with
this. McDonald Apache Point and the
regular use Apollo LLR. See, so that's 4. 1, 2, 3, 4.
4 observatories that are not associated with NASA.
Yeah,
so
exactly. NASA independent. Yeah. Oh, McDonald is independent. I thought it might not be. Yeah, it is. You're right. Well spotted. I'll have to point that out when I'm making the video on this.
Yeah,
I'm gonna basically do this as a presentation in a video. I'm gonna go for it reasonably quick. But I just want to, it's good looking at it with you guys just to spot because that's the key point, isn't it? It's NASA independent, as you say.
Yeah.
And then I think the fact they deployed these, which we've got pictures of, which we've bounced stuff off, which we've got scientific results of, which we've got boxes of stuff that people have they haven't faked all this just for fun, have they? They haven't built this whole observatory. Look, they didn't build that for fun and then put this laser in there for fun, did they? And then make these special detectors for fun, and then make this box, as a fake, and then make this. Do you see what I mean? And then do these experiments for years. It's just it's just a nonsense.
Yeah, they've been doing this shit for 40 years.
For 40, 50 years. Exactly.
50.
Yeah, exactly.
And have professional astronomers spend their whole life toiling over this.
Exactly, their whole career looking at this stuff. Exactly. That's what I want to do in the video. Is I want to make sure that message comes through clearly, because I really do think these flat earthers dismiss stuff.
Can you imagine being a young 22 or 23-year-old engineer just graduated from MIT or somewhere, and you get a job at this McDonald Observatory, and you spend the rest of your life looking at doing this stuff. It's your whole working life.
Yep.
And the thing is that you're very likely to stay doing that stuff for your entire life, because there's probably only 4 observatories in the world that are doing this sort of thing at this sort of level, and your background means that this is where you're going to be working, doesn't it? In all probability.
There we go, Ken. I'm firing the laser at the screen.
Ow! Jesus Christ, man! It's right in my eye, jackass.
Exactly. See, look, that doesn't have much of an effect, does it?
Hey, fuck
wow.
you.
Cool. Yours is much stronger than mine. Look at that. You're really.
I'm blinded.
You guys trying to
out laser each other.
Screw
our cameras up.
Webcams up.
I think Ken's laser is a bit more powerful than mine is. Mine's just a little low power little one.
Mine's bigger than yours.
Our size doesn't matter.
It will kill you. It will kill your sensor if you keep doing it.
What I did the other day was this. There's this quantum experiment where you put up. I don't know if you've seen it. Polaroid. Have you seen it? Where you take 3 sheets of Polaroid, and by inserting one in the middle, instead of removing light, it actually increases the light. Have you seen that? It's a quantum experiment.
Yeah, you put the cross polarizers in, and then you put the
it's actually a
polarizer in it, and it will actually turn the other 2 polarizers on.
Yeah, it's unbelievable.
You don't actually end up with more light out, but you end up with it not really, with it pretty much negating the cross polarizer effect.
I'm seeing your fingers, not the polarizer. Put it in front of your camera.
Yeah, I know. I'm trying to get it. Here we are. I'm trying to get it so it's. Can you see the polarizer? Yeah. I don't know if you actually probably put white paper behind it, and then if I put it in, can you see it's negating it?
Well, I can see you now. Yeah, it's negating it.
See that?
Getting the angle right. I think you've got the angle not. Yeah, you probably
I need to put this thing white behind it, probably.
A bunch of weird people.
They're trying to do online, trying to do spur of the moment experiments. Okay. Exactly.
I don't know if you can see the white. I probably need a little brighter thing behind me, don't I? Let's. You got your ball there, Ken?
Mm-hmm.
How do I actually get it onto my... Yeah, there we go. Right, I can see more. Right, there we go. Oh, that's better.
That ball looks flat.
And you sound, Tootie.
Yeah, exactly. I am. Younger than I sound as well, eh? You cheeky devil, John. You cheeky devil. Ka-ching! I like doing these ad hoc experiments, though. I like this stuff.
That's it. That's it, Ken. I'm going to get demonetized.
What did Ken just do?
Just showed his belly.
Oh, dear.
Oh, shit.
The camera just wrong.
That's it. Look. I'm going to get...
Come on,
I
John.
remember starting at the university in September '92, and being introduced to the Sun Lounge, which was the university's Sun Unix workstation lab, which had some really nice 28-inch monochrome monitors on there running X on these Sun workstations.
Sun workstations, because Sun did used to be the one. Is that just very quickly? Is that fake color that we're seeing, John?
So that's about as accurate as I could get it. So that's the California Nebula, which is a hydrogen alpha region. This is the Heart and Soul Nebula, both hydrogen regions.
I was amazed. I went and saw some amateur astronomers with some pretty good kit, and some of the images they showed me, I'm like, "Are these color enhanced?" He's like, "No." I was like, "The greens, the reds." I just couldn't believe them.
That's the Seven Sisters there, the Pleiades, and
that's not you not messed with that at all. That's literally a photo, is it?
I can't remember exactly how it. I think that's probably an hour. Maybe it says actually. Yeah, 16 5-minute frames.
16.
So that's
stitched together, yeah.
So that's stitched. They're just stacked on top of each other. So it's this 16 pictures of the same thing stacked together like a deck of cards.
So when you look through the telescope, you wouldn't actually see that. You'd have to do that time lapse to stack it, would you?
Well, this is actually just with a camera. It's a Canon 6D with a 24mm lens.
So that's not for a telescope. That's just a camera.
Yeah. So, yeah.
How did you zoom in so close to whatever that is that you the Pleiades? Did you say it was?
Yeah, well, it's
sisters. I can't remember what you said it was.
Yeah, it's the Pleiades, the Seven Sisters. But that's like a 20-odd megapixel image from a 66D.
The thing, I've been doing them time-lapse videos, Toady, that I've been on. Yeah. That's actually a much bigger. That's an even bigger field of view than my time-lapse pictures.
So these field of views you're talking about. So what magnifying lens have you got on your Canon there, John?
That's a 24mm lens, which is quite wide. So I mean, to give a ballpark comparison, if you held open a broadsheet newspaper at arm's length,
yes,
that's kind of roughly the field of view that you're looking at there. So I don't know if you know your constellations, but
nope, definitely not.
Nope.
That's Cassiopeia.
I heard of it.
That's Auriga.
So you do these things in this 20. This is where I always get confused with this photography. I hear, it magnifies 50 times, blah blah blah. That I think of in magnification, which I kind of vaguely understand. This 24mm stuff, you're losing me, John.
What
am I missing? Why is my brain always going to magnification, not this wide angle stuff?
It's effectively negative magnification.
Right.
Yeah, so a 50mm lens is pretty much representative of what you can see. And so if you go to half that, then you're seeing half the field of
field of view.
That's wrong. Twice the field of view.
But when I look up with my eyes at the sky, John, I do not see that. I've never seen anything that looks like that. I don't think.
That's because your eyes can't do a long enough exposure.
Well, the reason why I took that image in particular is this is the thinnest part of the Milky Way, and I wanted to see what would. And it's through a light pollution filter as well. It's from a very light polluted area where I used to stay. But I mean, it's a how long is that? 16 times 5 minutes. So it's an hour odd. The camera. It's not a high ISO, 800 ISO.
So if my eyes could compound light over half an hour, and I stood looking at half of it, that's what I'd see, is it? So that you're not magnifying that, you're not zooming in to get that picture, is what I'm getting at, I suppose.
No, you're zooming it out to make it wider. So you've got twice the field of view that you would normally see.
Yeah.
So 50. So for example, 50 is 1 times.
Yeah.
Yeah. So when I put my 600mm lens on, that's 600 divided by 50 times magnification, essentially, when you're looking through the viewfinder. So that's 600 divided by 50. Yeah, it's 12 times magnification. If I put a 6mm lens on, that would be negative 12 times magnification, because it would be 12 times wider.
Wow, look at that. So how come the moon's not in that? That looks very broad.
That's actually east is there and west is there. This is a 180-degree panorama. So it's made of, I think it's made of 5 like vertical shots. If you know what I mean, stitched together.
So you've stitched them, or you've taken 5 half-hour shots and then moved them across. How's that?
No, they're. I think these were quite short. I think they were maybe 12 or 15 seconds or something.
Oh, really?
15 seconds at ISO 12800. But with
12800, is that a fast speed? Is it?
It's basically making the camera more sensitive. All you're doing when you increase the ISO is turning up the gain. It's like turning up the volume, if you know what I mean.
Yeah, so you're grabbing a lot of light there. Yeah, look at that light pollution behind on the horizon, or is that not light pollution?
Totally. What you're doing is you get a certain amount of light and a certain number of random hot pixels and stuff. And what you're doing is when you turn up the ISO, you turn up everything.
So that's
Jupiter, the signal, and you turn up the noise.
So you're getting more light.
Jupiter there, Saturn.
You're getting the same amount of light. You're just amplifying it in the camera.
Okay.
Yeah. So there's 2 ways of doing it. You can amplify it using an analog amplifier before the sensor digitizes it, or you can turn it up in the sensor you can turn it up digitally by multiplying the numbers that you've already got by some factor.
Yeah. Wow, that's amazing as well. That's a phenomenal shot, John.
I haven't finished it yet.
What is it?
It's well, the green stripes are air glow, which is a sort of cousin of the Aurora Borealis. It's I'd never actually seen it before. I was really pissed off because I thought they were clouds. It was. And
did they look like that when you saw them, John, or only when you've done all this treatment?
Not as bright as that, but I could see them. But I think it's the way that it's formed is there's always air glow in the sky, but I think it's oxygen that's split by solar radiation into molecular oxygen, and then when the sun goes down, it recombines and gives off green light, I think.
But this almost looks like it's green and almost purple to me.
Well, that's the Milky Way. This bit.
Right. Okay. This is a high resolution image. Right. Okay.
And this is made of that was this 24mm lens, and there's there's probably about 3 pictures. Three
you put these into various competitions or something, because that to me is a stunning photo, right? Because you've got that lovely bit of green just on that hill, so it almost looks like it could be dawn, though I suppose it isn't. It's nighttime, I guess. And then you've got that reflection in the lake, and it almost looks like the hill is green, and then you've got that green, whatever you said, oxygen. It's just quite incredible.
Is it's the difficulty with these shots? I mean, this is the reason I hadn't finished this yet. And I took this in February. The difficulty is that they're quite long exposures. So I think there were 2 minute long exposures that for the sky and the loch were tracked, and then you've got to turn the tracking off and do your exposure for the land.
Right. And sorry, explain what you mean by tracked. I'm missing an understanding there.
Oh, sorry. I've got an equatorial mount that just goes on a camera tripod.
Yep.
So I can take long exposures with the camera without the stars trailing.
Without all the stars trailing. Right. Yeah. Okay. Okay. So it's moving with the equatorial mount. Long exposure while the stars are moving. Got it. Yep.
So that's why the landscape's all smudged. That's how
much.
Yeah,
it is all smudged. Yes.
So that's how much it's moved during the exposure. And that was a car. There's a road going down there.
How can the land move?
Well, the equatorial mount basically completely subtracts the rotation of the Earth.
Yep.
So in effect, the camera isn't moving, but the Earth continues to move. If you know what I mean. So
I need to think about that. You're trying to negate the stars moving. You're trying to keep up with the stars, aren't you?
In the length of time of the exposure, either you lock the camera to the Earth and you see apparent movement in the stars, or you lock the camera to the stars and you see the apparent movement in the
Earth. Right. Okay. So then you've got to take a normal picture of the loch and then blend it in with that skyscape.
Yeah, it's quite difficult to do, but I think this is an unprocessed image of just the foreground. Yeah, so that's if you just took a long exposure, capturing nicely the landscape. That's how far that's what the stars do. So you've got to take different separate exposures for the ground and for the sky, and then put them together. But it was bloody freezing that night. The tripod actually froze to the shore.
Oh, really?
Yeah, it was. Oh man, it was freezing. That's the east end of Loch Venacher, near Callander in the Trossachs. That hill is Ben Leddy.
I quite actually like the effect it's giving. Actually, now I'm looking at it to the land. I quite like that effect. Actually, that kind of makes it look slightly ghosty, doesn't it?
Yeah, and I think that's straight out the camera. I don't think I've done anything. Yeah, so you do need to. What I do basically is, see here. See that?
See where? I can't see where you're pointing. Where am I looking?
Am I?
I can't see.
I'm not. I'm not presenting. Hang on a sec.
No, you are presenting. We just don't necessarily see your mouse.
I didn't realise what it was doing. Hang on.
Oh yeah, I can see your mouse now.
Hang on a sec. So I've changed my screen, but I didn't realise I was that you guys couldn't see it. There we go. So that's a static picture of the land. Can you see that?
I'm trying to move it up a bit and across a bit. Right. Static picture of land, and look, the stars are all trailing a bit. So that must have been a long exposure. Yeah.
Yeah. So they were like a couple of minutes long. So the North Celestial Pole is up here somewhere, and the stars are moving from that direction.
Well, the Earth's moving, and it makes the stars look like they're moving.
The
trees come out really well. Look, silhouetted against the sky. They're fantastic. Those trees. Again, what resolution image is this?
Well, this is that's one image that's about it's 21 megapixels.
Oh, big image then.
So remember the original image was much bigger than that. So I stitched them together using a program called PTGI. But see these spots here.
What, that purple one?
Yeah.
Oh yeah, I see that, and another one. There's another one in the middle of the trees. Yeah. Oh yeah, and one there. Yeah, I see them.
They're hot pixels, so they're defective pixels that aren't working properly, which is another thing that you kind of want to try and remove as well. So it is actually worth taking dark frames to register what the camera sees in the absence of any light signal coming into the camera.
Like a lens cap on type situation.
You offer that to the software and say, subtract that from the image, please, and it does.
Right.
But yeah. I'll just another one.
They're quite impressive photos, John. I'm surprised at how easy it is to get such good photographs.
It's not easy.
Okay. So this is like work of quite a long while, is it? Because I'm just thinking, I'm going to get out there tonight with my Canon, bang it on some mount, point it at the stars, put on some long exposure with a high ISO, and I'm just going to be getting these kind of photos. It's not going to be like that, then I take it.
No. Well, it's
I'm joking, obviously. I'm joking, right? I'm not that stupid.
I'm trying to think how can I? Oh, there we go. Can you guys see my screen?
We could, and then it's vanished now.
It's just
maybe
loading.
It's loading.
So this is I haven't properly processed this either.
Oh.
But that's, can you see that?
Yeah, hang on, just let me keep adjusting my screen. So hang on, don't be zooming in. I'm trying to see it because it's got the horrible thing at the bottom as well. What's happening on my thing? I have to keep clicking on the screen to zoom in. There we are. Got it. Right. Don't move. Sorry. God. I seem to have inadvertently lost everything. Where's it all gone?
Can anyone else see my screen?
Yeah.
Yeah.
I seem to have somehow managed to lose the Hangouts, but you can still hear me, right?
I can hear. I can hear.
Okay, that's really very odd. Okay. What have I done? I've somehow managed to lose everybody, but you guys can still hear me, so that's good. I've lost all of John's stuff. I wondered if I'm trying to find what I had open, but I've obviously swiped something in my haste. Yeah, and lost it. Okay. Were we in Hangouts? Was that what we were actually in?
What the fuck?
How have I managed to lose everybody?
We're still here. We're still here.
I know, you can say that you can hear me. I'm going in a Hangout and it says there's no call connected. You can still hear me, which is a little bit odd.
Well, we always hear you.
I don't have any audio now.
There we go. I've only been half listening. I think I caught some of what was going
on.
Jesus, what have I done?
Are you having some IT problems, Tony?
I am. I can't believe. Right, you can still hear me. I'm still talking to you.
Yeah.
I've got Chrome open. Right. If I go into Hangouts, it says there's no calls in Hangouts, and I've got a new tab up. And yet you can still all hear me. Right. This is just a bit. I'm hoping it doesn't just drop off, but I'm just wondering how it can do that. I'm just. It's all right. I'm back. Oh, I see what it's done. Yeah, I see what it's done.
God, you're a flat earther.
Yeah, what it's done is it's zoomed in. It's fine. It's yeah. God knows how I do that. Right. I'm back. Don't worry.
You never left.
All is good.
You never left.
I never left. I know. I just wanted to get John's picture. What I was trying to do is take a. You're presenting to everyone. Oh, that's you, John. What I was trying to do was sort of frame it in the middle to see it, because John's screen on mine comes out skewed. I don't know if it's doing that for you guys. Maybe it's perfect for you guys. But mine, I've got this funny thing on the right. Is that on John's screen or isn't that on my screen?
John is presenting, it says.
Okay, have you got this massive, like half the screen taken up with a lot of people's icons very large?
No, not on your side.
All right, I've clicked something, haven't I? Okay, let me try and find John. Where's John? John. And to see his screen, I click on...
His icon.
His icon. I've done that.
Yeah, double click his icon.
I've done that. What I've still got is this, like, half the screen's taken up with... I don't know, I'd call it this extended sidebar.
I know what you mean.
Anyone know? Yeah. Any way of getting rid of that?
On the black bit of you got any black bit of screen around anything like a black bit of background?
Yeah. Well, yeah. That's the thing that's taking up about a quarter of my screen at the moment.
Double click on that.
Okay. That's done very little.
Okay.
Okay. Let me try at the bottom. I probably opened up. So I changed layout. Hang on. There we go.
Yeah, I knew it was something like that.
Spotlight. Yeah, it's fine. What I've done is inadvertently changed it. It's perfect now, John. It's perfect now. Sorry about that.
Glad to be of help, whatever we did.
Yeah. Well, you inspired me to double click on whatever the layout was, and that fixed it. So that's always good.
So I know what fixes it. Turn it off and then back on again.
Ah, yeah. Well.
This is just like the further down the lock.
I can see the schoolboy error here. Look at the reflection. You pick the star trails up in the reflection, and yet your equatorial mount has worked. Hang on, why didn't the equatorial mount work for the reflection as well, John?
It's a funny effect because this is a really wide angle. It's quite a wide angle lens.
Yeah.
You're looking here. You're looking right up the lock, kind of due west.
Mm.
But on this side, you're looking more towards kind of northwest.
Mm.
And there's a constant. It wasn't a still. The water wasn't still. There was a constant little swell in the water. So instead of the stars being points of light, they've drawn a line as the reflection bounced up and down as the waves came towards me.
Oh, so it's not. So if it was still, then the equatorial mount would also have made the reflection look correct as well. Then is that right?
Yeah, if it was like a mill pond, you would get points of light.
You'd still get points as well. I'm just trying to imagine, you know what I mean, how the equatorial mount would cope with the reflection. But of course,
it would just be the same.
It would be the same, right? So I was thinking that's what happened, but I see it's not. It's literally because the water's bouncing.
Yeah, I was quite a bit confused as to why it looked like that initially, but it's just constantly the stars are drawing a line on the sensor rather than.
It looks still. I mean, the image looks still. You know what I mean? The reflection looks a nice reflection, by the way.
Yeah, you get the green ribbon.
How in such a low light condition do you get so much color in this image?
Well, it's just a long exposure. I mean, it was pitch black when I was there.
What kind of phone do you? What kind of cell phone do you have?
Sorry.
What kind of cell phone do you have, as far as smartphone?
A Huawei Mate something or other.
Yeah, I was surprised at the camera settings I could pull off on my Galaxy 8. I got some sky shots. They don't come anything close to yours, but I was really surprised about I could get out of it.
Well, what I've got to kind of process this a bit to get it to jump out the way it does. I mean, it's you've got. I haven't added anything to it, put it that way, but you've got to turn up the saturation of the color, and it's like adjusting the contrast and color on your television kind of thing, you know.
Do you do that before you're taking the photo, or do you get the raw image and then treat it?
I shoot in raw, camera raw, and I don't do anything to it in the field at all.
Okay, all right, okay.
And then just see what happens when I get home. And there's also in Photoshop, there's actually an application called Camera Raw, and it's got lens profiles in it. And you can say, right, I'm using a 6D, I'm using a Samyang 24mm lens, and it knows the spherical aberration of all the lenses and how much vignetting, how much darkening you're going to get around the edges, and it fixes it.
Oh wow!
Which is quite handy as well. But yeah, it's a really laborious process. It's and there's lots of, most of the time when I go out, I come back with nothing at all. And you just got to be really stoic about it and just say, well, there's always tomorrow. And it can be really frustrating.
How did you learn to start taking photos like this, though? Where would you, enthusiastic amateur, tell them to start, right? So I've got an SLR, digital SLR. It's a Canon, whatever I said, 110D or something like that, right? So it's not a bad camera. Yeah. What image should I start with? Not trying to get a sky shot like that, but even just to understand how the light, I'm capturing more light than there may immediately appear to me to be. Just wondering what kind of.
Not like this.
If you've got,
you start by breaking it.
There's a rule I think called the 500 rule for taking pictures of stars. Which basically means whatever the focal length of your lens is, you divide 500 by it, and that gives you the number of seconds that you can take an exposure for without noticeable star trailing. So if I had a 50mm lens, I could take 10 seconds, a 10-second exposure.
Right, so if you've got a 50mm lens, you divide by 500 and you can take 10-second exposure.
Yeah, I mean, if you want it to be really high quality, I would divide 300 by the focal length of your lens, but 500 is not bad.
Mm-hmm.
Am I still presenting or not? I'm not sure.
No, there's nothing here.
Resume.
I can pin you. Oh, no, yeah.
So I guess what I'm suggesting, John, is it possible for me to, I don't know, take a picture of some cars outside, or should I start with the sky? You know, just to try to get an idea of how the light is working with the exposure length.
Shoot the sky with this. Mm-hmm. You need a remote shutter control for your camera, though. Really, ideally. Or
okay, why is that? Why do I need a remote shutter control?
Well, if you move it if you move the camera when you're pressing the shutter, then it'll appear on the exposure.
Am I not letting it automatically take the shots? Or maybe misunderstanding how I'm going to be using
you could possibly take a time lapse here where you would start the camera after a time, set a time.
If you touch the camera, you risk movement or vibration.
Yeah, and you do get with if you've got a fairly new DSLR, you can actually get an app on your phone, and you can control the camera completely through your phone, which is pretty good. Camera Connect, I think it's called, for Canons, which I used actually for that. The one where the picture we were looking at was the hill, the big hill in the background. But yeah, I would try just taking some 20-second exposures and just use an ISO of like 1600 or something. And
hang on, let me jot that down. Hang on a sec, because that sounds like at least a formula that I could start to try. Let me just find my book. And let me look up John Watson in it. I've got a page for everyone, so I've got a John Watson page. It's pretty empty at the moment.
My page will be empty.
Am I going into your black book?
Yeah, it is black. You are absolutely right. It's got Quantum Eraser's got about 27 pages. Rumpus has got a few, but John hasn't actually got an entry yet. But was it 1600 ISO and 20 seconds? Yeah.
Yeah. Can you remember what focal length your lens is? How many millimeters the lens is?
Shall I go and grab my lens and I'll have a look? Just hang on one sec, John. Just hang on.
Yeah.
Right, let's have a look. Where would it say on it? Oh, God, it appears to have a macro on it. I'm sure I didn't put a macro. Maybe it's got a built-in macro as well. So where would I look? Sorry, to find it. It's a Canon lens.
It should just say on the side in white letters.
So it says a number of things. It says EFS 18 to 55 millimeters. I don't know what that
so it's an 18 to 55 zoom lens.
Right.
So if I was you, I would wind it right down to 18. That's the widest angle that you've got.
I can get on this, right?
And at 18, it will have the widest f-stop. It'll have the widest aperture as well, I would imagine. Can you see what it says? If you've got like f numbers, like a small f and like f2.8 or f4?
I can't see any f's on it, which is, are they normally on a Canon lens somewhere?
Yeah.
Oh, hang on, I'm looking at the front. Yeah, hang on. Canon zoom lens, that's not very helpful. EFS 18 to 55, 1:3.5 minus 5.6. What's that mean?
What was the number before 5.6?
So it's, hang on, it's 1:3.5, then like a dash 5.6.
So if you've got it wound right out at 18 mil, you'll have it at f 3.5, which is not bad. So it should automatically just do that if you wind it out to 18 mil.
3.5. Okay, perfect. Yeah.
18 mil, and so that'll give you the widest field of view. So you divide 500 by 18, and that will give you the number of seconds.
So, quick question: isn't 55 mils bigger than 18? Why am I winding it down to 18? That sounds like it's smaller than 55 in numeric terms.
18 will give you the widest field of view. So 55 will be roughly kind of what you see with your eyes, and 18 will give you a wider field of view than
wider than our eyes. Right, we were talking about that earlier. Okay, right.
But importantly, the thing is that if you've got a zoom lens like that, if you zoom into the maximum zoom at 55,
yes,
you'll be shooting through a smaller aperture. And you don't want that. You want to let as much light into the camera as
possible. Right. Okay. I mean, obviously, this is just a general consumer lens. They probably sell with it as a startup kit to get you going, don't they? It's like a best of all worlds. Yeah, which is what they probably do. Yeah.
I've got an image. I think this was taken with that lens. This was a 28 to 90 kit lens with a Canon. Am I still presenting?
Yep.
So this was taken 2 kilometers south of Princes Street in the centre of Edinburgh through a light pollution filter.
Oh wow!
That's the Andromeda Galaxy.
Oh wow!
In fact, the Triangulum Galaxy is there as well. But that again, that was tracked though. That was tracked.
That was tracked, so you had time for it to be moving across.
Yeah, so it's probably about an hour or something. But yeah, if you do 18 mil, whatever that seconds that comes out to, you're dividing 500 by 18. If you want it super sharp, divide 300 by 18. And I would suggest an ISO of at least 1600.
At least. Okay, and then I can experiment with that going down. Yeah.
I would. Well, I mean, just as Alan was saying, the ISO is what you're doing is you have ISO 100 or 200. That's the native sensitivity of the camera. When you increase the ISO, all you're doing is you're amplifying it, and it gets grainier and grainier and grainier and grainier the higher the ISO is. You're not increasing the sensitivity. You're amplifying what you have.
Okay, what setting do I want? The Canon's got this. I don't know. There's a green thing, then it's got a P, TV, AVM. It's got all these different things. Then something that looks like a flower, something that looks like a bit like a landscape. Which of those settings?
If you've got I would put it on manual.
Manual. Okay, M. Not
either M or B for bulb.
B. There's no B there, so it'll have to be M.
Yeah, and your exposure is not. It'll probably go up to 30 seconds, but your exposure is going to be less than that, probably.
So my ISO goes down to 6400, 3200, and then 1600, like you say. Then I've got f-stop. It says of whatever you just said earlier. 5. No, it's showing 5 points. I've not wound it. Hang on, I've not wound it back. Yeah, hang on. I need to wind it back, don't I, to 18?
Yeah.
No, it doesn't seem to have changed, even though I've gone to 18.
What camera is it?
It's a Canon, whatever I said before. What was it? 110D, is it? Hang on.
On the
yeah, so it's 2 ones. It's 1100D.
You've got a digital display just behind the shutter button, do you?
Digital display behind the shutter button. Yeah, I mean, it's got a digital display on the back of the camera. I mean, it's a Canon DLSR. It's a 1100 is it EOS?
Yeah. If you just look, there'll be a function button where you can actually select the f-stop and wind it down to the smallest number it'll go to. So if you just look in the manual, and it sounds
Find
like
where that is. Yeah.
It'll go down at 3.5. I think you said it on the lens. To just get what you're doing there is you're widening I can't remember what it's called. There's a what's it called? You know, like in the sci-fi movies, you've got these circular doors with all the leaves that come in.
Oh yeah, I know, like the iris in and out. Yeah.
Yeah. So when you're selecting f3.5, you're widening that aperture as wide as open as it'll go for that lens. But yeah, just checking the manual, and there'll be a function button to change that, and make sure it's as low as it'll go.
Okay.
And you should be able to use the app Camera Connect. I would imagine if it's a fairly new camera, or you need to get a remote shutter cable. You can pick one of them up on eBay for like probably less than 10 quid. Right. Or you can get fully remote, like wireless ones as well, which are quite snazzy. Or a thing called an intervalometer, but they're quite complex. I wouldn't bother with one of them at the start. And just take lots of pictures and just see what you get. And you'll be probably quite surprised at how much light pollution affects your images. Even if it feels dark, if you start taking long exposures, you'll see the effects of it.
Really? So I'll be surprised by that, you think?
Yeah. I mean, even if it appears to be really quite dark to your eyes, the camera will pick it up. Or you've got a city that's maybe 20 miles, 30 miles away. You can't really see it. You'll see this sort of glow on the horizon from the city. When I took that picture next to the loch, if I'd have turned around and shot towards the south, it would have been really quite polluted with light from Glasgow. But I was looking towards the Scottish Highlands when I took the picture, if you know what I mean.
Yeah.
I'm not sure what else I could suggest, but just take loads of pictures and you can see from the EXIF. Every time you take a picture, its name will be its name will probably just be a number. But when you look at them on a computer, you download them, you can see what ISO it was, what the f-stop was, what exposure time it was, and you can actually sort of evaluate what worked best. And kind of make sure that you're kind of actually learning what you're doing and
what I'm doing. Yeah, because that's what I need to do: take a few pictures and start to see how those things affect it, don't I?
Yeah.
It's very annoying that I cannot find this blink and get it down to this 3.5 malarkey.
I think it might be a button with a sort of asterisk or star. Maybe I can't remember.
That one. Okay.
What camera have you got, Toadie?
I got a Canon EOS 1100.
You can get that down. You can get that down to 30 seconds of exposure.
But
you can do longer than that if you do it manually using the bulb setting.
But it'll be your exposure time will be less than 30. I would say.
Yeah. I mean, the pictures that I did to do the time lapses that I've done, I shot that at 8 seconds at f2.8 and then I did it at ISO 3200.
Bulb. What's this bulb setting? I've just come across it by rotating this thing. What does bulb mean?
Well, if you've got a remote shutter, if you press and hold the shutter button, it'll take a picture for as long as you hold it down.
And you just flash the bulb on and off, and then that gives it light, does it?
No, it's not. It's nothing to do with light. It's just what it's called. If you press and hold, it'll take an exposure for as long as you're holding down the shutter.
Okay, so I've got that. I've understood how to play with that one. Okay, I need to find out how to change this f-stop malarkey. See, it's annoying. It's on 18, but
you roll back. You have you adjust the if you're in manual.
I'm in M. Yep.
If you're in M, you adjust the aperture using the back control. In fact, you have to hold a button down on the back, and then you can rotate the little wheel at the front.
Right. Do you know which button I hold down? No. Okay. Any idea what it might look like?
Hang on, Cody. You're quite lucky because you know Carl Edwards from Johannesburg in South Africa.
Not really.
Well, he lurks a lot in the chat.
Is this your camera, Tony?
Fortunately for you, Tony. Fortunately
not
for you,
quite. What is that one? That's a Canon Rebel you're looking at.
What's the number of it again?
Mine's an EOS 1100D.
Okay.
S. No D.
I have the.
So that one.
Yep. Looks pretty like that one. Yep.
That button there.
That star. Okay, let's try that star.
Have you got a ruler?
Yes,
a ruler?
Say
that again. Sorry, Alan. So I'm hearing two conversations.
So
when I press the star, the screen disappears. Unfortunately.
It disappears.
Yeah. So the seconds, there's that rotatey one that you were pointing to. In fact, that picture you got on the right. See that rotatey thing? That changes the timing, which is great. But I don't know how to move it.
If you press and hold that, and then roll that, you should change the f-stop.
I press and hold it. Unfortunately, it blanks the screen.
Tony, if you press and hold the AV, the button that says AV,
got that one.
That should allow you to change your aperture value.
You're a hero. Whoever did that. Yay! Happy days.
In the
Thank you very much. Whoever said that, right? So I need to write that down as well. Right. So hang on. It's hold AV. And then wind the rotary for f-stop. And I vaguely know what an f-stop is now. Certainly I understand a little bit more about what it's going to do. And then the other one is the ISO is rotate.
Totally. I'm planning on because I've had conversations with various different people. I think I'm going to do some hangouts where we all together and I take you through doing the settings and what they do on your DSLR camera.
Oh, that'd be a brilliant idea, wouldn't it? That would be a brilliant idea.
Because
because Canons are probably all reasonably similar.
Canons are all reasonably similar.
The fantastic thing is, if you put a Canon DSLR on a telescope, the only things that you can control is the ISO and the shutter speed, and that's it.
Hey,
you can't do anything else anyway. It makes it so much.
Really?
Yeah, I had to actually learn how to use a camera properly for when I started doing the landscape stuff. I didn't have a clue what I was doing.
You know, one of the big advantages of Canon over most of the other manufacturers, they set it up so that if the body thinks it hasn't got a lens attached to it, i.e. what you get when you put it on a lens with no electronic controls on it, it still allows you to use automatic exposure, because you can set it to AV mode, okay, and it will work out what the correct exposure is based on the amount of light coming into it. And in AV mode, you would set the aperture value anyway, so it doesn't care that it can't adjust the aperture, because it's automatically adjusting the shutter speed or the ISO to get the image correctly exposed. But most other manufacturers' bodies, when you do that, it goes wibble and refuses to play at all in auto exposure modes. So picking a Canon body is good, because you can pick up old manual lenses, so you can pick up an old wide angle.
So I could use an old Canon lens on this, could I?
The only ones you can't, the only manufacturer's lenses that don't really mount well on a Canon EOS line range are Canon lenses.
Right. Did I just hear that right?
Yes. Well, Canon's old manual lenses used to mount at the same distance from the film plane as the electronic lenses. And that is just about the closest distance for any lens for any Canon put the lens mount closest to the film plane, and they used the biggest throat opening. So what you can't do is you can't with a Canon manual lens, because that's basically got the same size bayonet and the shortest possible distance. There's nowhere to put the mount adapter, because you can't put it inside the mount, because the mounts although the opening is the biggest you can get, the Canon manual lens is also huge, so there's no room to put the metal of the mount adapter in between.
Oh, so I'd have to use an adapter, would I? If I went and bought a Nikon lens, or I don't know, just making up a lens that isn't a Canon.
If you picked up an old Nikon F series wide angle lens, then that mounts a little bit further forward, and it's basically not as wide. So you've got room for the mount adapter to fit in the gaps, because you've got to have a gap, and you And if you mount, the problem is if you mount the lens further forwards, right, it won't focus to infinity.
Right, so I couldn't go and find a really great old telephoto zoomy lens thing to like really do, or whatever.
I would suggest actually if for the purposes of astrophotography, that's all I can really speak about. I don't really know much about any other kind of photography, funnily enough. But you want a prime focus lens. You don't want a zoom lens, really.
Right. I'm just thinking of lenses that are expensive and they come up at auctions for like tuppence, right? I'm just thinking, I didn't realize I could put other lenses on this fella. Yeah, that's why
the lenses of choice of landscape, the stuff that I'm doing, is the Samyang 14mm or 24mm SAMYANG Samyang, and they're not very expensive. If money is no object, I would look at Sigma Art lenses. But
I'm
again,
not spending a lot on any lens at the moment until I got a decent picture. I'm just thinking, I go to auctions sometimes and I see loads of camera lenses, but never realised I could actually put them onto this, And they sell them quite often for tuppence, like ones that obviously, because the rest of it's actually just got an SLR in there, right, which no one wants to buy anymore, an old, film camera. SLR. Yeah, exactly. I mean, the market's dropped off that. And these are people who probably in 1990 bought, were probably our age, and spend a lot of money on it. Do you see what I mean? And now maybe quite old, and unfortunately have either passed on or certainly passed their stuff on. You know what I mean? It comes up at auction. No one wants to buy it. Yeah, I mean, just it gets chucked out almost.
But there's talking about prime lenses. There are quite old, like 50mm lenses that are they've got really good reputation even now, and you would be able to pick them up. There's a couple of websites actually. MPB, Mike Papa Bravo, MPB. I bought the lens that I used for that Loch Venacher shot from them secondhand, and it was flawless. Nothing wrong with it at all. I can't think of any others, but the MPB, they sell secondhand stuff and do trade-ins and stuff. They're pretty good. They give a really good honest appraisal of secondhand lenses and cameras. They're definitely worth it.
Could I quickly share? Could you stop sharing for just a second, John?
Well, as long as you look at my picture that's called Jupiter and Moons first.
Okay. Do that.
Can you see that picture?
I can see the moon.
Oh, yeah.
The title of the picture is Jupiter and Moons.
Yeah, I can see the moon. I can't see anything else. Where are they?
There's Jupiter and its moons, and plus our moon in the top.
I can see them. They're little.
And there's that up here.
So, yeah, that was my little astronomy joke, calling it Jupiter and Moons. Anyway.
When are you doing your course, Alan? Get to know your camera course. It's a good idea because it's a perfect way to do it on the. We can all hold our cameras and watch, online lesson.
Exactly. There you go. That's the 14mm lens that John was talking about.
Right.
Okay. And
there's a better one than that actually now, that like a new edition that's got less lens aberration. I think it's like called the XS, the Samyang 14mm XS or something. But yeah, I've got that lens.
Canon cashback.
Yeah, this is Warehouse Express in Norwich.
Oh, right, okay.
They are really good.
Canon lens reward. Save up to £855 on a body and selected purchases.
Because Samyang also do some, although Samyang are cheap lenses, they do some cinema video lenses, and their 16mm t2.6 cine lens for Canon fit £1,800.
What's the cine lens?
It's basically
it's at home. Sorry.
But when we talk about the aperture being an f value,
yeah,
and that's fine as far as it goes, but it doesn't allow for the actual amount of light that is not transmitted by, because obviously you get a certain amount of light reflection off every lens element, off both surfaces of it and what have you. So you lose a little bit of light going through it, but when you're doing cine, you can't control the exposure by using the shutter, because the shutter speed is fixed in proper real cine cameras. It's fixed by the frame speed.
Sorry, Terry, I hear you. Did you see Terry's message?
Yeah. Yes, I saw that. I shall stop. Once I finish this little bit, I shall stop. So basically, one of the things you have with cine lenses is they have, instead of having an f-stop, which is the ratio of the aperture diameter to the focal length, they have a t-stop, which is the f-stop plus the bit that the lens eats from reflections and what have you, because you have to know very exactly, because what happens is if you're going to have two cameras set up, you want to be able to know that the amount of light reaching the film is exactly the same, so that you can cut them together without changes in exposure, because you can see even a sixth of a stop of difference in exposure. So having the T stop allows you to know that the two lenses will transmit exactly the same amount of light for any exposure value, and that is a good thing, but that costs you lots of money.
Can I just say before Terry chucks us out, I've just put my email in the panel chat for anybody who wants to get in contact with me. Tori, if you've got any questions about what I've been talking to you about. Sorry to butt in.
That's okay. So yeah, that's why some of them are a bit more expensive. And what I should have done when I picked up these Samyangs was I should have done Canon EFS mount, because that will reduce the number of products we are looking at. So yeah.
Right, I'd better go. I've got inquisitive people. So thanks, John, for explaining about those lenses. I will definitely try a bit of the over the weekend, that astrophotography.
Which when do people think would be a good time to try and do this sort of sit down with the camera and deal with it? On a weekend or on
I think a weekend is best, because I think weekday might be a bit hard to guarantee. Weekend is good, isn't it? Because it'd be a couple of hours of sitting there and playing with all the different settings, wouldn't it? And
yes, and talking about what they do.
Talk about what they do exactly, and maybe even taking the odd photo, I suppose. Or
shall I try and find the time next weekend then?
Yeah, I think that's a good idea. I think you probably want to advertise it, trail it as well, Alan, because I think probably quite a few people might be interested.
That's why I said next weekend.
Yeah,
because I can trail it on my because also we can
get Jose to trail it. You see what I mean? Because I think you might get more people than you might be surprised. Hopefully.
Yeah, and
and it can be recorded as well, and then you can always put it out.
the other thing I was going to say was, if you join my Discord, which is on my, it's on the video descriptions now on the last few streams I've done, and I know pretty much everybody here is on my Discord. I'll put stuff on. I'll put stuff on there. People will be able to put. It'll help me by people being able to put some. This is what I want to know stuff up. Yeah. Question, because people put. I can have some questions in advance that I know people actually want to. What stuff people actually want to know, so that I can address it in the stream without having to do it cold off the top of my head necessarily. I can do a little bit of preparation, because the one thing I learned on my the one thing I did learn on my adult ed instructors course was preparation is key.
7 P's. You heard of that?
Yes, prior preparation prevents piss poor performance.
Yes. One more thing I would. Is Toady he's gone? Is he?
I think he might have done, because I think he had the problem I had earlier of people saying, "Pay attention to me now."
God damn it!
So so I think we better let Terry say goodnight to YouTube land and.
Yes.
Okay. Yeah, I'm still here.
He's still got 18 people watching. Poor bugger hasn't been tonight.
I've been nodding off a little bit, but I've been trying to listen too because I didn't want to miss out on anything.
Yeah. So, okie dokie. I've finished what I had to say, so I'll let Terry say goodnight for us.
Oh, okay. I'm asleep, so I'll just talk in me sleep then. Thanks for letting me share it over onto my channel, Alan. Even though that's a third. This is a third party. Thank you, like from Jose to you to me.
It was handy because we had that power cut as well here, so it would have, if it hadn't been for the streaming problems, I think we've had a few lightning strikes here earlier, which is what took the power down. So, and I think that was what was taking out my connection to YouTube, because everything else this end was fine. It was the link from the computer to YouTube that was the issue.
Oh, okay.
The meat was fine. Everything in the meat was fine, and of course I had people here and didn't notice because I was dealing with them. But never mind.
Yeah, never mind. It all worked out in the end.
It did indeed.
Okay then. So it's good night from me, and it's good night from him.
Good night from
us. All right. Cheers, Terry.
Cheers, guys.
Right.
Yeah. Good night.
I'll leave Rumpus in here.